We built the largest machine in human history to find a single particle. And the moment we found it, we realized we might have opened a door we cannot close. 50 years, 3 generations of physicists, a 27-kilometer ring buried beneath the border of France and Switzerland, pushing protons to within a whisper of the speed of light, smashing them together 14 million times per second. All to catch a glimpse of something that appears in roughly 1 out of every billion collisions. Something that exists for less than a trillionth of a second before it vanishes. Something that, according to the math, should not just explain mass. It should explain why anything in this universe has weight at all. On July 4, 2012, scientists at CERN announced they had found it. The Higgs boson, the particle that gives electrons their heft, quarks their substance, atoms their ability to hold together long enough to become stars, planets, and you. The discovery completed a puzzle that had been unfinished since 1964. It confirmed a theory so elegant, so precise, that its confirmation should have been the end of the story. But it was not the end. Because the moment we measured it, the moment we pinned its mass at 125 gigaelectron volts, a new question surfaced, a question no one wanted to ask out loud. What if the Higgs boson is not fundamental? What if this particle, the thing we spent half a century hunting, the cornerstone of mass itself, has parts? What if there is something smaller inside it, held together by forces we have not yet detected, operating at scales we cannot yet reach? If that is true, then everything we thought we understood about the fabric of reality just became a placeholder, and the real answer is still hiding. This is that story. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. The universe doesn't owe us elegance. It doesn't care if our equations are pretty or if our theories fit into neat boxes that humans can understand. But for a few extraordinary decades in the middle of the 20th century, physicists discovered something shocking. The universe was, in fact, speaking in math, and not just any math. Precise, predictive, almost unreasonably accurate math that described the behavior of the smallest constituents of matter with a clarity that bordered on the uncanny. They called it the Standard Model. By the 1970s, it had become the most successful theory in the history of science. It explained how particles interacted. It predicted the existence of things no one had ever seen, and then those things showed up in particle accelerators right on schedule. It unified forces that had once seemed unrelated. It took the messy, chaotic zoo of subatomic particles discovered throughout the mid-century and organized them into families with rules, symmetries, and relationships that made sense. And it had one catastrophic problem. The theory worked perfectly as long as every particle in it was massless. The moment you tried to give those particles mass, the math fell apart. The equations that described electromagnetism and the weak nuclear force, the two forces that had just been unified into a single framework, became nonsensical. Infinities popped up everywhere. Predictions stopped working. The symmetry that made the whole thing beautiful shattered like glass. This was not a minor issue. This was not a rounding error or a detail that could be addressed later. This was fundamental. Because in the real world, particles are not massless. Electrons have mass. Quarks have mass. The W and Z bosons, the particles that carry the weak force, have mass, a lot of it. The Z boson weighs about as much as a silver atom. For a subatomic particle, that is enormous. So here was the problem in plain language. The theory that explained the universe only worked if particles had no mass, but the particles in the universe definitely had mass. Something was missing. Something deep. For a while, physicists tried to patch it. Maybe mass could be added by hand, written into the equations as an initial condition rather than something the theory predicted. That didn't work. The moment you forced mass into the equations, the theory lost its predictive power. It stopped being a theory at all and became a collection of observations with no underlying logic. You could describe what was happening, but you couldn't explain why. And physics without why is just bookkeeping. By the early 1960s, the situation was becoming unbearable. The Standard Model was on the verge of being one of the great intellectual achievements of human civilization, and it was being held hostage by a single question it couldn't answer. How do particles that are born massless in the equations acquire the mass we measure in the real world? That question, by the way, is not abstract. Mass is not some vague property you can wave away. Mass is the resistance an object has to being accelerated. It's the thing that makes a rock harder to throw than a feather. It's what keeps planets in orbit and makes cars hard to stop. At the level of particles, mass is what allows matter to exist in a stable form. Without mass, electrons wouldn't bind to nuclei, atoms wouldn't form, chemistry wouldn't happen, you wouldn't be here. So when physicists in the 1960s stared at their equations and realized they couldn't explain where mass came from, they weren't puzzling over some footnote in an obscure paper. They were staring at a hole in the foundation of reality. The breakthrough, when it came, didn't arrive with fanfare. It came in the form of 3 separate papers published in 1964 by groups working independently, none of whom initially realized the others were onto the same idea. One paper was written by Robert Brout and François Englert in Belgium, another by Peter Higgs in Scotland, a third by Gerald Guralnik, Carl Hagen and Tom Kibble, working in England. All 3 groups proposed essentially the same solution to the mass problem, though they phrased it differently and emphasized different aspects. The idea was this: what if mass isn't a property particles are born with? What if it's something they acquire by moving through a field that fills the entire universe? Not a field in the sense of a meadow, a field in the sense that physicists use the word. An invisible, all-pervading presence that exists at every point in space. Electric fields and magnetic fields are examples. They're not made of particles, they're not objects you can touch, but they're real. You can measure them, you can feel their effects. A charged particle moving through an electric field experiences a force. The field is doing something to the particle. What Brout, Englert, Higgs and the others proposed was a new kind of field, one that didn't push or pull, one that resisted, a field that would slow down certain particles as they tried to move through it, giving them inertia, making them behave as though they had mass. The technical term for this process is spontaneous symmetry breaking. That phrase sounds like jargon, but the underlying concept is simple. Imagine a ball sitting at the top of a perfectly symmetrical hill. The hilltop is flat, and the ball could roll down in any direction. The situation is symmetric. There's no preferred direction, but the moment the ball rolls, the symmetry breaks. The ball picks a direction, and now the landscape looks different depending on where you're standing. In the case of the Higgs field, the symmetry that breaks is more abstract. It's a symmetry in the equations that describe how particles interact. In the early universe, when temperatures were unimaginably high, the Higgs field had no preferred state. It was symmetric. Particles zipping through it experienced no resistance. They were massless. Then the universe cooled, and at a certain critical temperature, the Higgs field underwent a phase transition, like water freezing into ice. It settled into a new state, a state where it was no longer symmetric, a state where it had a non-zero value everywhere in space. And from that moment on, particles moving through this field experienced resistance. That resistance is what we call mass. Peter Higgs, in his paper, took the idea one step further. If the field exists, he reasoned, then it should have a particle associated with it. All fields do. The electromagnetic field has the photon. The field describing the strong nuclear force has gluons. If there's a Higgs field filling the universe, there should be a Higgs particle. A quantum, a ripple, a localized excitation of that field that could, in principle, be detected. That particle would be the smoking gun. Find it, and you prove the field exists. Prove the field exists, and you've explained where mass comes from. Higgs submitted his paper to a journal called Physics Letters. It was rejected. The editor didn't think the idea was important enough. Higgs revised it, added a paragraph explicitly mentioning the particle, and sent it to another journal. This time it was accepted. The paper was published in October 1964. It was 2 pages long. For a while, almost no one noticed. The idea was too strange, too speculative. The notion that particles acquire mass by wading through an invisible field sounded more like philosophy than physics. There was no experiment anyone could think of that would test it. The technology to create and detect a Higgs particle didn't exist. The energies required were far beyond what any accelerator at the time could reach. The idea went into the literature and sat there, quietly waiting. It took nearly a decade for the physics community to realize what had been proposed. By the mid-1970s, the standard model had matured. The theory had been tested in experiment after experiment, and it kept working. Predictions matched observations with absurd precision. But the mass problem was still there, unresolved, lurking in the background like a crack in a dam. Then physicists started looking back at those 1,964 papers, and they realized something. The Higgs mechanism wasn't just a clever trick. It was the only known way to give particles mass without destroying the rest of the theory. If you wanted the standard model to work, you needed something like the Higgs field. There was no alternative. Suddenly, the idea wasn't speculative anymore. It was necessary. And if it was necessary, then the particle had to be real. Somewhere out there, hiding in the debris of high-energy collisions, the Higgs boson was waiting to be found. The problem was that no one knew where to look. The theory didn't predict the mass of the Higgs boson. It only said that the particle should exist and that it would couple to other particles in proportion to their mass. Heavy particles would interact with it strongly. Light particles would barely notice it. But how heavy the Higgs itself was, that was an open question. It could be light enough to have already been discovered. It could be so heavy that no existing accelerator could produce it. There was a range, a vast range, and somewhere in that range the answer was hiding. By the 1980s, physicists knew what they needed to do. They needed to build a machine powerful enough to search the entire possible mass range. They needed to smash particles together at energies high enough to briefly recreate the conditions of the early universe, when the Higgs field was still settling into its current state. They needed to look for the particle in the only place it could be found, in the fleeting instant after a collision, before it decayed into something else. That machine would take decades to build. It would require the cooperation of thousands of scientists from dozens of countries. It would cost billions of dollars and require engineering on a scale that had never been attempted. It would push the limits of human technology and human patience. And even then, there was no guarantee it would work, because the Higgs boson, if it existed at all, would be one of the rarest, most elusive particles in nature. Producing one would require not just high energy, but extraordinary precision and unimaginable amounts of data. The particle would appear in only about 1 in a billion collisions, and when it did appear, it would last for less than a trillionth of a second before disintegrating into a spray of other particles that detectors would have to catch and reconstruct. Finding the Higgs boson, in other words, would be like firing 2 bullets at each other, photographing the collision, sifting through a billion photographs, and identifying the one image where a very specific pattern of debris appeared that could only have come from a particle that existed for less time than it takes light to cross an atom. And they had to do it without knowing for certain that the particle was even there. This was the quest. Not to explore strange new worlds or to chart the cosmos, but to find a single particle whose existence would confirm that the universe is filled with an invisible field that gives meaning to the concept of mass itself. A particle that, until someone actually detected it, was nothing more than a consequence of equations written by a handful of physicists in 1964. The Standard Model, by this point, had passed every test thrown at it. Every prediction had been confirmed. Every particle it said should exist had been found, except one. The Higgs boson was the last missing piece, the final holdout, the one part of the theory that remained purely theoretical. And so the hunt began. It would take 40 years. It would involve false starts, near misses, and moments where physicists thought they had it, only to watch the signal dissolve into noise. It would require a machine so large it would have to be buried underground in a tunnel 17 miles around. It would demand detectors the size of apartment buildings and computing power that rivaled the entire early internet. But the question driving it all was simple: where does mass come from? Why does anything weigh anything at all? And is there really a field, invisible and universal, that reaches into every corner of space and touches every particle that moves through it? The answer was out there, somewhere in the data, somewhere in the noise, waiting. The Higgs field is not a thing. That is the first misconception to clear up, and it is the one that trips up almost everyone encountering this idea for the first time. When physicists say the universe is filled with a field, they do not mean the universe contains some kind of substance or fluid or gas. They mean something stranger. They mean that every point in space, every cubic centimeter of the void between galaxies, every atom of air in your lungs, every region of space-time, from the moment of the Big Bang to the heat death of the cosmos, has a number attached to it. That number represents the value of the Higgs field at that location, and in our universe right now, that number is not 0. If the Higgs field was 0 everywhere, particles would be massless. They would zip around at the speed of light, unable to slow down, unable to bind together, unable to form anything stable. The fact that the field has a non-zero value everywhere is the reason mass exists, the reason you exist. This is a hard thing to wrap your mind around, because fields in physics are invisible and abstract. You cannot see them. You cannot touch them. But you experience their effects constantly. The electromagnetic field is a field. It is not made of photons. Photons are excitations of the electromagnetic field, ripples in it, the way waves are ripples on the surface of water. The field itself is the deeper reality. The particles are just what happens when you disturb it. The Higgs field works the same way. The field is the fundamental thing. It exists whether or not you disturb it. The Higgs boson, the particle discovered in 2012, is what happens when you put enough energy into the field that it vibrates in a localized way. You whack the field hard enough with a particle collision and a ripple forms. That ripple is the Higgs boson. It lasts for about a 10,000th of a billionth of a second, Then it collapses back into the field, spitting out other particles as it goes. The field remains, always. So when you hear someone say the Higgs field gives particles mass, what they mean is this. As particles move through space, they are not moving through empty vacuum. They are moving through a medium. Not a physical medium like air or water, a field. And certain particles interact with that field in a way that slows them down, gives them inertia, makes them resist acceleration. That resistance is mass. The analogy physicists like to use is molasses. Imagine trying to walk through a swimming pool filled with molasses. You can move, but it takes effort. The molasses resists you. Now imagine that some people wade through the molasses more easily than others. A small child might slip through with only a little resistance. A large adult might struggle, pushing against the thickness with every step. The molasses is not adding weight to them in the traditional sense. It is interacting with them as they move, slowing them down in proportion to how strongly they couple to the fluid. That is roughly how the Higgs field works. Particles that interact strongly with the field, like the top quark or the W and Z bosons, acquire a lot of mass. Particles that interact weakly, like electrons, acquire very little. Particles that do not interact with the field at all, like photons, remain massless and travel at the speed of light forever. The molasses analogy is imperfect. For one thing, molasses is made of molecules. The Higgs field is not made of anything. It is a fundamental feature of space-time. For another, molasses slows you down through friction, a mechanical process involving atoms bumping into each other. The Higgs field slows particles down through a quantum interaction that does not involve friction in any conventional sense. But the analogy captures the essential idea. The field is everywhere. Some particles feel it more than others. The ones that feel it more behave as though they have more mass. Here is another way to think about it. Mass is not a property a particle carries around with it like a label. Mass is a relationship. It is the relationship between a particle and the Higgs field. An electron does not have mass because it is inherently heavy. It has mass because it interacts with the Higgs field in a specific way. If you could somehow turn off the Higgs field, the electron would become massless. It would shoot off at the speed of light and never stop. That sounds like science fiction, but it is not hypothetical. In the very early universe, before the Higgs field settled into its current state, particles were massless. The universe was a hot, dense soup of radiation and energy, and nothing had mass. Then the universe cooled, and something extraordinary happened. The Higgs field underwent what physicists call a phase transition. Think of water freezing into ice. Above 0 degrees Celsius, water is liquid. Molecules move freely. The system is symmetric in the sense that no direction is preferred. There is no structure. Below 0 degrees, water crystallizes, ice forms. The molecules lock into a lattice. The symmetry breaks. Suddenly there is structure, and there are preferred directions defined by the crystal lattice. The Higgs field did something similar. In the early universe, at extremely high temperatures, the field had no preferred value. It was in a symmetric state. As the universe cooled, the field dropped into a lower energy state, a state where it had a non-zero value everywhere. The symmetry broke, and from that moment on, particles moving through the field experienced resistance. They acquired mass. This is called spontaneous symmetry breaking. The word spontaneous does not mean random. It means the system chose a lower energy configuration without being forced into it by an external cause. The field settled into the state it is in now because that state is more stable, like a ball rolling down a hill and settling into a valley. The valley is not special in any absolute sense. There could have been other valleys, but once the ball settles, that valley defines the landscape. For the Higgs field, the valley it settled into determines the masses of all the particles in the Standard Model. The W and Z bosons, which mediate the weak nuclear force, acquire their masses directly from the Higgs mechanism. The quarks and leptons, the building blocks of matter, acquire their masses through a slightly different process called Yukawa coupling, where their interaction with the Higgs field is proportional to a number called the Yukawa coupling constant. That number is different for each type of particle. The top quark has a large Yukawa coupling, so it gets a lot of mass. The electron has a tiny Yukawa coupling, so it gets very little mass. Neutrinos have an even smaller coupling, so small that for a long time physicists thought they might be massless. They are not, but they are close. The Higgs field does not give mass to everything. It does not give mass to protons and neutrons, for example, not directly. Most of the mass of a proton comes from the energy of the quarks and gluons buzzing around inside it, bound together by the strong nuclear force. That energy, through Einstein's equation E equals mc squared, manifests as mass. But the quarks themselves, the fundamental particles that make up the proton, get their mass from the Higgs field. Without the Higgs field, quarks would be massless, protons would not exist, atoms would not exist, nothing would hold together. This is why the Higgs field is so important. It is not just an interesting curiosity, it is the reason stable matter exists. Without it, electrons would not stick around nuclei. They would fly off at the speed of light. There would be no atoms, no chemistry, no stars, because stars are held together by gravity, and gravity requires mass. No planets, no water, no life. The Standard Model, as elegant as it is, would be a sterile, lifeless theory without the Higgs field. A universe full of massless particles zipping around at light speed, unable to slow down, unable to interact in the complex ways that give rise to structure. The Higgs field is what allows the universe to have a history, to cool down, to form galaxies and stars and planets, to become interesting. Peter Higgs understood this. In his 1964 paper, he did not just propose a mechanism for giving particles mass. He proposed that the field responsible for this mechanism should have an associated particle, a quantum, a physical manifestation that could, in principle, be detected in an experiment. That particle would be a ripple in the field, created when enough energy was dumped into it to excite it above its stable, non-zero baseline. Finding that particle became the obsession, because fields are abstract. You cannot prove a field exists by looking at the sky or measuring forces in a lab. Fields reveal themselves through their effects. And the cleanest, most direct effect of the Higgs field would be the Higgs boson itself. Detect the particle, and you have proven the field exists, proven that this invisible, all-pervading entity is not just a mathematical trick, but a real feature of the universe. The problem was that the Standard Model did not predict the mass of the Higgs boson. It only predicted that the particle should exist, and that it should couple to other particles in proportion to their masses. Heavier particles would decay into the Higgs more often. Lighter particles would barely interact with it, but how heavy the Higgs itself was, that was an open question. Theorists could set rough bounds based on what they knew about the weak force and the behavior of other particles. Too light, and it would have been detected already in earlier experiments. Too heavy, and the theory would start to behave badly, producing nonsensical predictions. There was a sweet spot somewhere in the middle. Somewhere between about 115 and 180 giga-electron volts. A giga-electron volts is a unit of energy that particle physicists use as a stand-in for mass, thanks to Einstein. 1 giga-electron-volts is roughly the mass of a proton. That range was huge. It meant physicists needed to build a machine capable of searching across that entire spectrum. A machine that could produce collisions energetic enough to create a particle anywhere in that window. And even then, they would have to sift through billions of collisions to find the few where the Higgs briefly flickered into existence before vanishing. The Higgs boson, if it existed, would be the second heaviest fundamental particle in the Standard Model. Only the top quark, discovered in 1995, would be heavier. And the top quark was already pushing the limits of what accelerators could produce. Creating a Higgs boson would require even more energy, even more precision, and even more patience. Here is what made the search especially difficult. The Higgs boson does not hang around. Its lifetime is about 1/10,000th of a billionth of a second. In that time, it does not travel any measurable distance. It decays in place, almost instantly, into a shower of other particles. Detectors cannot see the Higgs directly. They can only see what it decays into. And because several different processes can produce similar-looking debris, identifying a Higgs decay requires reconstructing the collision, measuring the energies and angles of all the particles that came flying out, and checking whether their combined properties match the signature predicted by theory. To make things worse, the Higgs boson is rare. According to CERN, it appears in only about 1 in a billion proton-proton collisions at the Large Hadron Collider. 1 in a billion. That means you need to produce billions of collisions and record every single one in enough detail that you can later go back and identify the handful that might contain a Higgs. Then you need to analyze all that data, filter out the noise, and look for a small bump in the distribution of events at the mass where the Higgs should be. A bump that could just as easily be a statistical fluctuation. This is not like finding a needle in a haystack. It is like finding a specific needle in a haystack the size of a mountain, where the needle looks almost identical to 10 million other needles that are not the one you are looking for, and you have to examine each one individually to determine whether it is the right needle or not. And you cannot do it with one collision, or 100, or 1,000,000. You need so many collisions that the statistical noise averages out and the real signal, if it exists, rises above the background. Physicists talk about sigma. A 1 sigma result means the signal is about as strong as the random fluctuations you would expect from noise. A 2 sigma result is a bit more convincing. 3 sigma is interesting. 4 sigma is exciting. 5 sigma is the threshold for claiming a discovery. 5 sigma means there is only about a 1 in 3.5 million chance that the signal you are seeing is a fluke. That is the standard particle physics uses because history is full of 3 sigma results that disappeared when more data came in. Getting to 5 sigma requires enormous data sets, millions and millions of collisions. Detectors that can measure particle trajectories and energies with exquisite precision, computers that can process petabytes of data, and years of running the machine at full power. In the 1980s, when physicists started planning the experiments that would eventually find the Higgs boson, they knew all of this. They knew the particle would be rare, short-lived, and hard to distinguish from background noise. They knew they would need a collider more powerful than anything that had ever been built. They knew they would need detectors the size of buildings, filled with millions of sensors, each one calibrated to measure particles passing through at nearly the speed of light. They knew they would need a global collaboration involving thousands of scientists from dozens of countries. They knew it would take decades. And they knew there was no guarantee the particle was even there. The Higgs mechanism was the best explanation anyone had for why particles have mass, but it was still just a theory. A very compelling theory, yes. A theory that fit all the data. But until someone actually detected the Higgs boson, it remained a hypothesis, an educated guess, a placeholder for something deeper that no one fully understood. So why build the machine? Why spend billions of dollars and decades of effort chasing a particle that might not exist? Because the alternative was worse. If the Higgs boson did not exist, then the Standard Model was incomplete in a fundamental way. Something else had to be giving particles mass, something the theory did not account for. And finding out what that something was would require going to even higher energies, building even larger machines, searching even longer. But if the Higgs boson did exist, if the field was real, then humanity would have answered one of the oldest and deepest questions in physics. We would have explained why the universe is the way it is, why matter is stable, why stars burn, why chemistry works, why atoms hold together, why you have mass, why anything has mass. The Higgs field, invisible and intangible, is the scaffold on which the structure of reality rests. Without it, the universe would be a featureless storm of massless particles and radiation. With it, the universe becomes a place where complexity can arise, where particles can slow down, clump together, form structures, interact in intricate ways, build galaxies, stars, planets, cells, brains. The field is not magical. It does not care about you. It does not care about life. It does not care about anything. It is a consequence of the laws of physics playing out in the specific configuration our universe happens to occupy. But the fact that it exists, that it settled into a non-zero state billions of years ago when the universe cooled past a critical temperature, is the reason you are here reading this. Every electron in your body has mass because it interacts with the Higgs field. Every quark in every proton, in every atom in your cells, acquired its mass the same way. The carbon, the oxygen, the nitrogen, the calcium, every element that makes you alive, exists only because particles with mass were able to slow down and bind together under the influence of forces that only work when particles have mass. The Higgs field is not the only field in the universe. The electromagnetic field, the gluon field, the quark and lepton fields, all of them fill space in similar ways. But the Higgs field is different. It is the only fundamental scalar field in the Standard Model. Scalar means it has no direction. The electromagnetic field has a direction. It points from positive charges to negative charges. The Higgs field just is. It has a value at every point in space, and that value is the same in every direction. That simplicity is part of what makes it so strange. Most fields in physics are dynamic. They change, they wave, they interact with themselves in complicated ways. The Higgs field, in its ground state, does nothing. It just sits there with a non-zero value, filling the universe, waiting for particles to move through it. When physicists finally built the machine capable of testing whether this invisible, all-pervading, perfectly still field was real, they were not building it to satisfy curiosity. They were building it to complete a theory that had been under construction for more than 50 years. A theory that explained almost everything about the subatomic world, but left one enormous question unanswered: the question of mass, the question of why anything weighs anything at all, the question of why the universe is not a formless void, but a place where structure, complexity, and eventually consciousness could emerge. And so the machine was built. In a tunnel 17 miles in circumference, buried beneath the border of France and Switzerland, engineers and physicists assembled the most complex scientific instrument ever constructed. It would take protons, accelerate them to within a whisper of the speed of light, and smash them together 14 trillion times per second. And in the debris of those collisions, somewhere in the cascades of particles flying out in every direction, the Higgs boson would be waiting, if it existed at all. The theory was beautiful, the field was invisible, the particle was hypothetical, and none of it mattered unless someone could actually build a machine capable of testing whether any of it was real. By the early 1980s, physicists knew what they needed. They needed to recreate the conditions of the early universe, the moment just after the Big Bang, when particles were slamming into each other with enough energy to shake the Higgs field hard enough to produce its particle. They needed to accelerate protons to nearly the speed of light, smash them together, and sift through the wreckage looking for a signal that would appear in perhaps 1 out of every billion collisions. They needed detectors sensitive enough to track particles whose lifetimes were measured in trillionths of a second. They needed computers powerful enough to process data flowing in faster than the entire early internet could handle. And they needed to do all of this with a precision that would make a watchmaker weep. They needed, in other words, to build something that had never been built before. Something so large, so complex, so far beyond the edge of existing technology that even describing it sounded like science fiction. They needed the Large Hadron Collider. The location had already been chosen. CERN, the European Organization for Nuclear Research, sits on the border of France and Switzerland near Geneva. It was established in 1954 as a collaboration between 12 European countries who wanted to rebuild their scientific communities after the devastation of World War II. The idea was simple: pool resources, share knowledge, build machines too expensive for any one nation to afford alone. By the 1980s, CERN had become the world's leading center for particle physics, home to a series of increasingly powerful accelerators that had discovered the W and Z bosons, confirmed the existence of gluons, and mapped the behavior of quarks with extraordinary precision. But the machine CERN had been using, the Large Electron-Positron Collider, was reaching the end of its useful life. It had done its job. It had tested the standard model to exquisite accuracy, but it was not powerful enough to find the Higgs. Electrons and positrons, the particles it collided, were too light. They did not carry enough energy to push into the mass range where the Higgs was expected to hide. To reach higher energies, you needed heavier particles, protons. Protons are messy. Unlike electrons, which are fundamental particles with no internal structure, protons are composite objects made of quarks and gluons. When you smash two protons together, you are not colliding two clean points of matter. You are colliding two chaotic bundles of subatomic junk, each one a roiling mess of particles constantly appearing and disappearing in a quantum foam. Most of the time, the collision just scatters the debris. But every so often, a quark from one proton hits a quark, or a gluon from the other, at just the right angle, with just the right energy, and something interesting happens. A new particle forms. A Higgs boson, maybe, or a top quark, or a dozen other exotic things that only exist for fractions of a second before decaying. Using protons meant the collisions would be noisier, harder to interpret, more statistically messy, but protons could be accelerated to much higher energies than electrons. And higher energy was the only thing that mattered. If the Higgs boson was hiding at 125 giga-electron-volts, you needed a machine that could deliver that much energy in a single collision. The Large Electron-Positron Collider could not do it. A proton collider could. So in the early 1990s, CERN began planning the Large Hadron Collider. Hadron is just the physics term for any particle made of quarks. Protons are hadrons, so are neutrons. The name was generic on purpose. The machine would spend most of its time colliding protons, but it could also accelerate heavier ions if scientists wanted to study the behavior of matter under extreme conditions. The design was audacious. The machine would be built in the same tunnel that had housed the Large Electron-Positron Collider, a circular underground ring 27 kilometers in circumference, carved through the rock beneath the French and Swiss countryside. Protons would be accelerated in opposite directions around the ring, bent into a circular path by thousands of superconducting magnets, and steered into head-on collisions at 4 points around the ring where massive detectors would be waiting to record what happened. 27 kilometers. To put that in perspective, if you stood at one point on the ring and started walking, it would take you more than 3 hours to walk all the way around. The tunnel itself sits between 50 and 175 meters underground, carved through a mix of sandstone and molasse that geologists had mapped in exquisite detail before construction began. When the tunnel was originally excavated for the previous collider, the two teams digging from opposite directions met in the middle with an error of less than 1 centimeter. 1 centimeter over a distance of 27 kilometers. That is the kind of precision engineers were working with from the beginning. The heart of the machine is the magnets. Protons are electrically charged, so they can be pushed and steered using electromagnetic fields. But bending a proton beam moving at nearly the speed of light into a 27-kilometer circle requires an absurdly strong magnetic field. Ordinary electromagnets would not cut it. You would need so much electrical current to generate the necessary field strength that the magnets would melt. The solution was superconducting magnets. Magnets made from special alloys that, when cooled to temperatures just a few degrees above absolute zero, lose all electrical resistance. Current flows through them without losing energy, and the magnetic fields they produce can reach strengths far beyond what any normal magnet can achieve. The LHC uses 9,593 magnets. Most of them are small correction magnets, tweaking the beam in tiny ways to keep it on track. But the workhorses are the 1,232 main dipole magnets, each one 15 meters long and weighing in at about 27 tons. These dipoles generate the magnetic field that bends the proton beam around the ring. They operate at a field strength of 8.3 Tesla. For comparison, a typical refrigerator magnet is about 0.005 Tesla. The Earth's magnetic field is about 0.0005 Tesla. These magnets are more than 100,000 times stronger than the planet's natural field. To reach that strength, the magnets have to be kept at 1.9 Kelvin, that is 1.9 degrees above absolute zero, colder than outer space, colder than anywhere in the known universe, except inside a laboratory. The entire 27-kilometer ring is essentially a giant cryogenic system, the largest in the world, filled with 96 tons of liquid helium that keeps the magnets at their operating temperature. If the cooling system failed, the magnets would quench, a term that sounds gentle but describes a catastrophic event where the superconducting coils suddenly develop resistance, the stored magnetic energy turns into heat, and the magnet can be destroyed in seconds. The protons themselves do not start in the LHC. They begin their journey in a much smaller machine. Hydrogen gas is stripped of its electrons, leaving bare protons. Those protons are fed into a linear accelerator that boosts them to about 50 million electron volts. From there, they move into a circular accelerator called the proton synchrotron booster, then into the proton synchrotron, then into the super proton synchrotron, each machine accelerating the beam to higher and higher energies before finally injecting it into the LHC. By the time the protons enter the main ring, they are already traveling at more than 99% the speed of light. The LHC's job is to push them the rest of the way. Inside the ring, the protons are organized into bunches, tight clusters of about 100 billion protons each. The LHC can hold up to 2,808 bunches circulating in each direction. That is roughly 6 trillion protons in total, split between two beams moving in opposite directions. The beams do not fill the tunnel. They are threaded through a vacuum pipe about the width of a soda can. The vacuum inside that pipe is one of the best vacuums ever created, with a pressure 10 times lower than on the surface of the Moon. This is necessary because even a stray molecule of gas could scatter a proton out of the beam, and at the energies involved, a single proton carries enough kinetic energy to damage the equipment. Each proton in the beam makes 11,245 laps around the ring every second. At that speed, the protons are moving at 0.999999991 times the speed of light. Not 99%, not 99.9%, 99.9999991%. The difference between that speed and the speed of light itself is so small that a proton traveling around the ring for 1 second gains only about 3 meters on a photon traveling the same path. At these velocities, time dilation becomes a real, measurable effect. For the protons, time is running about 7,000 times slower than it is for the scientists watching them. A proton that would normally decay in a microsecond can survive for milliseconds simply because, from its perspective, time has slowed to a crawl. Getting the beams up to full energy takes about 20 minutes. Once they are stable, the operators begin the delicate process of steering them into collisions. At 4 points around the ring, the vacuum pipes merge, and the beams are focused down to a width narrower than a human hair. As the proton bunches pass through these crossing points, a tiny fraction of the protons collide head-on. The collision energy is enormous. Each proton carries 6.8 tera-electron volts of energy, so a head-on collision delivers 13.6 tera-electron volts. That is roughly the kinetic energy of a flying mosquito compressed into a region smaller than a single atom. For a fraction of a second, in a space far too small to see, the temperature and energy density inside that collision zone match the conditions of the universe a trillionth of a second after the Big Bang. The LHC produces about 1.5 billion collisions per second in each of its two main detectors. 1.5 billion per second. Most of those collisions are boring. The protons just graze each other, scatter some quarks and gluons, and produce a spray of low-energy particles that the detectors ignore. But a few collisions, a tiny fraction, produce something rare, a W boson, a Z boson, a top quark, and very occasionally, a Higgs boson. The detectors are where the magic happens, or rather, where the extremely careful, painstaking, and statistically rigorous analysis happens. The LHC has 4 main detectors positioned at the collision points around the ring. The two largest are Atlas and CMS, both general-purpose detectors designed to look for a wide range of particles, including the Higgs. The other two, ALICE and LHCb, are specialized instruments designed to study specific kinds of physics. Atlas and CMS are the ones that mattered for the Higgs search, and they are engineering marvels in their own right. Atlas, the larger of the two, is 46 meters long, 25 meters tall, and weighs about 7,000 tons. It is the largest particle detector ever built. CMS is smaller but denser. It is 21 meters long, 15 meters wide, and weighs 14,000 tons, twice the mass of Atlas, despite being half the size. The reason CMS is so heavy is its magnet, a superconducting solenoid that generates a magnetic field of 4 Tesla and is surrounded by about 10,000 tons of iron. 10,000 tons, that is more iron than the Eiffel Tower. Both detectors are built like onions, with layers of different sensors surrounding the collision point. The innermost layer is a tracking detector, a region filled with millions of tiny sensors that record the paths of charged particles as they fly outward from the collision. Particle tracks curve in the magnetic field, and by measuring the curvature, physicists can determine each particle's momentum. Outside the tracker is the calorimeter, a dense wall of metal and sensors designed to absorb particles and measure their energy. Electrons and photons are stopped in the electromagnetic calorimeter. Heavier particles, like protons and neutrons, are stopped in the hadronic calorimeter. Outside all of that is the muon detector, because muons are the only charged particles that can punch through the calorimeters without being absorbed. By the time a particle reaches the muon detector, it has passed through meters of steel and instrumentation. If it is still moving, it is a muon. The detectors do not see the Higgs boson directly. They cannot. The Higgs decays in about 1/10,000th of a billionth of a second, far too quickly to travel any measurable distance. What the detectors see are the particles the Higgs decays into, 2 photons maybe, or 2 Higgs bosons that immediately decay into 4 leptons, or a pair of bottom quarks that hadronize into jets of particles spraying outward in opposite directions. Each decay channel has a distinct signature, a pattern of energy and particle types and angles that can, with enough statistics, be distinguished from the background noise of ordinary collisions. The problem is volume. The detectors are recording 1.5 billion collisions per second. Each collision generates terabytes of data, tracking every particle, every energy deposit, every trajectory. There is no way to store all of that. The detectors would fill 50,000 1-terabyte hard drives every year if they saved everything. So instead, the detectors use a trigger system, a set of ultra-fast algorithms that decide in real time which collisions are interesting enough to save. Most collisions are discarded instantly, thrown away before they are even fully recorded. Only about 1 collision in a million makes it past the trigger. Those collisions are saved to disk, shipped to CERN's data centers, and distributed across the worldwide LHC computing grid, a network of computing centers in more than 40 countries that work together to analyze the data. This is not a small operation. The grid is one of the largest distributed computing networks in the world, processing petabytes of data every year. It has to be. Finding the Higgs boson requires analyzing billions of collisions and looking for a tiny statistical excess at the right mass, a bump in the data. A place where slightly more collisions than expected produce a certain combination of particles with a certain total energy. That bump, if it exists, is the Higgs, but you cannot see it with 100 collisions, or 1,000, or 1,000,000. You need so many collisions that the random fluctuations average out and the signal, if it is real, rises above the noise. The detectors were built by international collaborations involving thousands of scientists from dozens of countries. Atlas has about 3,000 physicists. CMS has about 4,000. The 2 experiments are deliberately kept separate. They analyze their data independently, use different techniques, different software, different statistical methods. The idea is that if both detectors see the same signal, you can be confident it is real. If only one detector sees it, it is probably a fluke. This redundancy is critical in a field where a statistical fluctuation can easily look like a discovery until more data comes in and the signal disappears. Building the detectors was as difficult as building the collider itself. Atlas was too large to be assembled on the surface and lowered into the cavern, so it was built underground in pieces and assembled in place. The cavern it sits in is 35 meters wide, 55 meters long, and 40 meters tall, carved out of solid rock. The excavation alone took years. CMS was assembled on the surface in 15 slices, each weighing more than 1,000 tons, and lowered into its underground cavern using custom-built cranes. One of the slices, the central barrel, was so heavy and so precisely balanced that it took an entire day to lower it the 100 meters into the cavern without damaging the sensors inside. The scale of the project was staggering. The LHC cost about $8 billion to build, with $531 million contributed by the United States. That is a lot of money for a machine designed to do one thing: collide protons. But it is not just a machine, it is an instrument, a microscope for looking at the fabric of reality at scales far smaller than atoms, a telescope for peering back in time to the first moments after the Big Bang, a testbed for ideas that have been sitting in textbooks for 50 years, waiting for someone to check whether they are right. And it was not built by one country or one institution. It was built by a collaboration of nations, an alliance of physicists and engineers who agreed that understanding the universe was worth the cost. CERN itself is funded by 23 member states, but scientists from more than 100 countries work there. The LHC is humanity's machine, not Europe's, not CERN's. It belongs to the species. That might sound grandiose, but it is true. The data is public, the discoveries are shared, the knowledge gained is not proprietary or classified. It is added to the sum of human understanding and published for anyone to read. When the LHC was finally completed, when all 9,000 magnets had been installed and cooled and tested, when the vacuum system had been sealed and pumped down, when the detectors had been assembled and calibrated and the computing grid was ready, the engineers did something simple. They turned it on. The first beams circulated on September 10, 2008. Protons were injected into the ring, accelerated to a modest energy, and steered around the full 27 kilometers without incident. Champagne was opened, speeches were made, the machine worked. 9 days later, a faulty electrical connection between two magnets caused a catastrophic failure. The connection overheated, melted, punctured the helium cooling system, and released 6 tons of liquid helium into the tunnel. The pressure wave damaged 53 magnets. The machine was shut down for more than a year while repairs were made and safety systems were upgraded. It was a humbling reminder that even the most carefully engineered systems can fail in unexpected ways. But by late 2009, the LHC was back online. This time, there were no catastrophic failures. The beams were brought up to higher energies. Collisions began. Data started flowing into the detectors. And the search for the Higgs boson, which had been theoretical and hypothetical and mostly a matter of writing papers and making predictions, became experimental. The machine was ready. The detectors were ready. The physicists were ready. All that remained was to run the collider long enough to collect the billions of collisions needed to answer the question: does the Higgs boson exist? Is the field real, or is the standard model, for all its successes, missing something fundamental? The LHC had been built to find out, and it would, but not right away. Because the Higgs boson, even in a machine this powerful, was still the rarest and most elusive particle anyone had ever searched for. And before the machine found it, before July 4, 2012, when the discovery was announced to the world, physicists would spend decades chasing hints and shadows and signals that appeared and then vanished. The hunt had just begun, and it would take longer and demand more patience than almost anyone expected. The machine was ready. The detectors were humming. The proton beams were circulating at nearly the speed of light, and physicists around the world settled in for what they knew would be a long, patient hunt for a particle that might not even exist. Except this was not the first hunt, not even close. By the time the Large Hadron Collider came online in 2009, the search for the Higgs boson had already been going on for decades, and it had been going badly. The Higgs mechanism was proposed in 1964. The particle, if it existed, should have been detectable the moment accelerators reached high enough energies to produce it. Simple, right? Build a bigger machine, smash particles together, watch for the Higgs to appear. The problem was that no one knew exactly how much energy would be enough. The theory predicted the particle should exist. It did not predict how heavy it would be. And that missing number, the mass of the Higgs boson, turned what should have been a straightforward search into a multi-decade game of hide-and-seek played across 3 continents with machines that cost billions of dollars. The first serious attempt to find the Higgs boson began at CERN in 1989 with a machine called the Large Electron Positron Collider, LEP for short. This was the LHC's predecessor, built in the same tunnel that would later house the Proton Collider. LEP was elegant in a way the LHC is not. It collided electrons and positrons, particles that are fundamental, meaning they have no internal structure. When an electron and a positron collide, they annihilate completely, converting their mass and kinetic energy into pure energy. That energy can then materialize as other particles, depending on how much energy is available. If you had enough energy, a Higgs boson could pop out. LEP ran for 11 years. It was a clean machine, producing collisions that were easier to interpret than the messy proton smash-ups the LHC would later specialize in. Electrons and positrons are point particles. When they collide, you know exactly how much energy went into the collision and exactly what came out. There is no background noise from stray quarks and gluons bouncing around inside composite particles. If LEP had produced a Higgs boson, the signal would have been crisp, clear, unmistakable. It never did. LEP searched across the entire mass range it could reach, from about 80 giga-electron volts up to about 115. The detectors watched millions of collisions. Physicists analyzed the data, looking for the characteristic signature of a Higgs boson decaying into pairs of other particles. Bottom quarks, tau leptons, W bosons. The signatures were well understood. The analysis techniques were solid. The data was clean, and there was nothing. No Higgs, not at 80 giga-electron volts, not at 90, not at 100. As LEP pushed to higher and higher energies, the search continued and the silence grew louder. Then, in the year 2000, something strange happened. Just before LEP was scheduled to shut down to make way for the LHC, one of the detectors, a machine called Elusive, picked up a handful of events that looked like they might be Higgs decays. The mass, if the signal was real, was around 115 giga-electron volts, right at the edge of what LEP could reach. The other 3 detectors, Delphi, L3, and Opal, saw hints too, not strong signals, just faint whispers in the data. A few more events than you would expect from random chance. The physics community went into overdrive. If the Higgs was sitting at 115 giga-electron volts, LEP could find it. They just needed more time. A few more months of running, a bit more data, and the signal might strengthen into a discovery. CERN's management faced a decision: extend LEP's run and delay the construction of the LHC, or shut it down as planned and move forward. They extended the run. LEP kept colliding electrons and positrons through the end of 2000, squeezing every last collision out of the machine before it was finally permanently shut down in November. The final data came in. The signal did not strengthen, it faded. The handful of events that had looked like a Higgs boson turned out to be a statistical fluctuation, the kind of thing that happens when you sift through millions of collisions looking for a rare event. Sometimes the noise lines up in a way that looks like a pattern. It was not a pattern. It was noise. LEPI shut down without finding the Higgs. The tunnel was emptied. The electron-positron collider was dismantled. And the final word from LEPI was this: if the Higgs boson exists, it is heavier than 115 giga-electron-volts. That was it. A lower limit. A line in the sand. Useful, yes, but not a discovery. Not even close. Meanwhile, across the Atlantic, another machine was hunting the same particle. The Tevatron, located at Fermilab near Chicago, was the most powerful particle collider in the world through the 1990s and early 2000s. Unlike LEP, the Tevatron collided protons and antiprotons, accelerating them to energies of about 1 tera-electron-volt per beam. That was higher than LEP could reach, which meant the Tevatron could search for a Higgs boson in a mass range LEP could never access. The Tevatron had two main detectors, CDF and D0, both designed to sift through the debris of proton-antiproton collisions looking for rare events. The detectors were smaller than the ones that would later be built for the LHC, but they were sophisticated, packed with sensors and surrounded by magnets and calorimeters capable of reconstructing the trajectories and energies of the particles flying out of each collision. The Tevatron produced collisions for more than 25 years, from 1983 until 2011. For a long stretch of that time, it was humanity's best shot at finding the Higgs. It came close. The Tevatron's energy was high enough to produce Higgs bosons if the mass was in the expected range. The detectors were capable of identifying the decay signatures. The collaborations were large, well-funded, and staffed with some of the best experimental physicists in the world, and for years they saw nothing. Just like LEP, the Tevatron sifted through millions of collisions, analyzed the data, and came up empty. No clear signal, no discovery. Just upper and lower bounds that slowly tightened as more data came in. By the mid-2000s, the situation was getting uncomfortable. The Higgs boson, if it existed, was running out of places to hide. LEP had ruled out everything below 115 giga-electron-volts. The Tevatron was pushing into higher masses, ruling out chunks of the allowed range one by one. Theorists were watching nervously because the standard model only worked if the Higgs mass was within a certain window. Too light, and earlier experiments would have found it. Too heavy, and the theory started to break down, producing predictions that did not make sense. There was a sweet spot, a narrow range where the Higgs could exist without breaking the math, and that range was shrinking. Then, in 2011, just months before the Tevatron was scheduled to shut down, both CDF and D0 announced something, not a discovery, not even a strong hint, just an excess. A small statistical bump in the data around 120 to 140 giga-electron-volts. The signal was not strong enough to claim a discovery. It was barely 2 sigma, meaning there was about a 1 in 20 chance it was just a random fluctuation, but it was there. And it was sitting right in the mass range where the LHC was starting to search. The Tevatron shut down in September 2011. Its final data was still being analyzed when the LHC results started coming in, and for a brief moment there was hope that the two machines together might converge on a discovery. The Tevatron's data could confirm what the LHC was starting to see. That did not happen. The Tevatron's signal was too weak. The statistics were not good enough. What the Tevatron had found was not the Higgs boson. It was a whisper of a possibility that might have been a Higgs boson if you squinted hard enough, and added more data that no longer existed because the machine had been turned off. This is what the search looked like for almost 30 years. Hints, near misses, statistical fluctuations that appeared and then disappeared. Signals that looked promising until more data came in and revealed them to be noise. It was not that the experiments were poorly designed or that the physicists were incompetent. It was that the Higgs boson, even when you are smashing particles together at enormous energies, is breathtakingly rare, and when it does appear, it does not hang around. The Higgs boson has a lifetime of about 10 to the power of negative 22 seconds. That is a decimal point, followed by 21 zeros, and then a 1. To put that in perspective, light, the fastest thing in the universe, travels about 30 centimeters in 1 nanosecond. In the lifetime of a Higgs boson, light does not even make it across the width of a single proton. The Higgs appears and vanishes in a span of time so short that it might as well not have a duration at all. You do not see the Higgs boson in a detector. You cannot. It decays before it has time to move any measurable distance. What you see are the particles it decays into, and you have to reconstruct what happened by looking at the pattern of debris flying outward from the collision point. That debris can come from a lot of things. A Higgs boson decaying into 2 bottom quarks produces a signature that looks almost identical to dozens of other processes that have nothing to do with the Higgs. A Higgs decaying into 2 photons is cleaner, easier to identify, but also much rarer. The problem is statistical. Out of every billion proton-proton collisions at the LHC, only about 1 produces a Higgs boson, 1 in a billion. And when that one Higgs does appear, it decays in one of several possible ways, each with its own probability. The cleanest decay channels, the ones that are easiest to identify, are also the rarest. You are not just looking for a needle in a haystack. You are looking for a specific kind of needle, one that appears only occasionally, in a haystack the size of a mountain, where most of the other needles look almost exactly like the one you want. So you collect data, billions of collisions. You filter out the obvious junk, the low-energy scatters, the events that are clearly not interesting. You save the collisions that might contain something rare. Then you analyze them, one by one, reconstructing the particles that flew out of each collision, measuring their energies and trajectories, checking whether their combined properties match what you would expect from a Higgs decay. Then you do it again, and again, and again, millions of times, until you have enough data that the statistical noise averages out and the real signal, if it exists, starts to emerge. This is not fast. This is not glamorous. This is years of work, performed by thousands of people, most of whom will never be named in the press releases. The scientists who design the detectors and the ones who calibrate them. The engineers who keep the accelerator running and the technicians who replace broken sensors. The software developers who write the code that filters and analyzes the data. The graduate students who spend months or years working on a single analysis, checking and rechecking their results, looking for errors, looking for biases, looking for any reason their signal might not be real. This is what a particle physics experiment looks like at this scale. It is a collaborative effort involving thousands of people spread across dozens of institutions in more than 40 countries, all working together toward a single goal: find the Higgs, or prove it does not exist. By 2010, the LHC was starting to ramp up. The machine had recovered from its 2008 failure and was colliding protons at energies LEP and the Tevatron could never reach. The first collisions were cautious, low-energy runs designed to test the machine and the detectors, but by early 2010, the LHC was running at 3.5 tera electron volts per beam, 7 tera-electron-volts total collision energy. That was already higher than the Tevatron, and it was just the beginning. The plan was to push to even higher energies once the machine proved it could handle the load. The data started pouring in, not a trickle, a flood. The LHC produces about 1.5 billion collisions per second during a typical high-intensity run. The detectors cannot save all of that. There is not enough storage in the world. So the trigger systems, the ultra-fast decision-making algorithms built into the detectors, filter the data in real time, keeping only the collisions that look interesting and discarding the rest. Even after filtering, the amount of data is staggering, petabytes per year. The worldwide LHC computing grid, the distributed network of computers that processes the data, was handling more information than most of the early internet ever saw. Inside that ocean of data, the signal was hiding, a small excess of events at a specific mass. Not enough to be obvious. Not enough to jump out of the noise. Just a slight uptick, a bump in the distribution, the kind of thing you could easily miss if you were not looking for it. And even if you saw it, you could not trust it. Not yet. Statistical fluctuations happen. 3 sigma signals have appeared and vanished before. The only way to know if a signal is real is to collect more data and see if it gets stronger. If it is real, more collisions will produce more Higgs bosons, and the bump will grow. If it is noise, the bump will wash out, smoothing back into the background as the statistics improve. The Atlas and CMS collaborations were designed to be independent. Same machine, same collision energy, but different detectors, different teams, different analysis methods. The 2 groups did not share their data with each other during the search. The idea was simple. If both detectors see the same signal at the same mass, you can be confident it is real. If only one sees it, it is probably a fluke. This redundancy is critical. It is the difference between a discovery and a mistake. And in particle physics, where statistical flukes can look exactly like the thing you are searching for, redundancy is the only defense against being wrong. By mid-2011, both Atlas and CMS were starting to see something. Not a clear signal, not yet, but an excess. A small clustering of events around 120 to 130 giga-electron-volts. The kind of thing that makes you pay attention but does not let you celebrate. The data was still too sparse. The statistics were not good enough. A 2 sigma signal is interesting. A 3 sigma signal is exciting. But 5 sigma is the threshold for discovery, and they were not there yet. Not even close. And then there was the added pressure. The Tevatron had just shut down after seeing its own faint hint in roughly the same mass range. LEP, more than a decade earlier, had seen something at 115 giga-electron-volts that turned out to be nothing. The history of the Higgs search was littered with signals that evaporated under scrutiny. No one wanted to be the team that announced a discovery only to watch it dissolve into noise 6 months later. So they waited. They collected more data. They refined their analyses. They checked and double-checked their results. And the tension built. The LHC was not just a machine. It was the culmination of decades of work, billions of dollars, and the careers of thousands of scientists. If the Higgs boson was real, this machine would find it. If it was not real, this machine would prove it. There was no third option. The Standard Model, for all its successes, had one missing piece, and that piece had been missing since 1964, 47 years. An entire generation of physicists had spent their careers searching for this particle. Some had retired without ever seeing it. Others had built their reputations on the assumption that it existed. If the LHC found nothing, the implications would be enormous. It would mean the Higgs mechanism, elegant and mathematically compelling as it was wrong. Something else was giving particles mass, something the theory did not account for, and figuring out what that something was would require going to even higher energies, building even larger machines, starting over from scratch. But if the LHC found the Higgs, if the signal was real, it would be the vindication of 50 years of theoretical work. It would complete the Standard Model. It would confirm that the universe really is filled with an invisible field that gives particles mass. It would answer one of the deepest questions in physics, and it would do so in a way that was measurable, repeatable, and undeniable. The stakes, in other words, were about as high as they get. And by late 2011, the data was starting to look promising. Both Atlas and CMS were seeing an excess around 125 giga-electron volts. The signal was faint, still not strong enough to claim a discovery, but it was there, and it was growing. Every week, more collisions. Every month, more data. The bump in the distribution was becoming harder to ignore. CERN scheduled a seminar for December 2011. Both collaborations presented their latest results. The room was packed. Physicists from around the world watched the presentations, studying the plots, analyzing the numbers. The signal was not 5 sigma, not yet, but it was stronger than it had been. Atlas reported an excess around 126 giga-electron volts, with a significance of about 2.3 sigma. CMS reported an excess around 124 giga-electron volts, with a significance of about 2.6 sigma. The two numbers were close enough that they could be pointing at the same particle, but not definitive, not yet. The message from CERN was cautious. The results were intriguing. They suggested the possibility of a Higgs boson in that mass range, but more data was needed. The LHC would continue running through 2012, collecting more collisions, refining the measurements. If the signal was real, it would strengthen. And if it was real, both detectors would see it clearly by the middle of the next year. That is where the search stood as 2011 turned into 2012. Decades of effort, billions of collisions, thousands of scientists, and a faint signal, barely visible above the noise, sitting at 125 giga-electron volts. It might be the Higgs boson. It might be the biggest discovery in particle physics in a generation, or it might be nothing. Another statistical fluctuation, another near miss in a long history of near misses. The only way to know was to keep running the machine, keep collecting data, and wait for the statistics to tell the story. The LHC had been built to answer a single question, and after nearly 50 years, the answer was finally within reach. By early 2012, the whispers had turned into something louder, not quite a shout, but definitely more than background noise. The Atlas and CMS collaborations had both seen something in their December 2011 presentations. A bump in the data, sitting right around 125 giga-electron volts. The signal was not strong enough to call it a discovery, not yet. But it was strong enough to make physicists cancel their vacation plans and start running the LHC harder than it had ever been run before. The machine had been designed to reach collision energies of 14 tera-electron volts. That was the goal, the full power, the setting where the LHC would be most likely to produce rare particles like the Higgs boson. But in 2011 and early 2012, the machine was running at lower energies, first 7 tera-electron volts and then 8 tera-electron volts, because the engineers wanted to be cautious. The 2008 failure, when a faulty connection had released 6 tons of liquid helium into the tunnel and damaged 53 magnets, was still fresh in everyone's memory. Push too hard, too fast, and you risk breaking the machine. Run too cautiously, and you might never collect enough data to see the signal you are looking for. By the spring of 2012, the decision was made. Run the machine as hard as safely possible, maximize the number of collisions, flood the detectors with data. If the Higgs was real, if the signal at 125 giga-electron-volts was more than just a statistical fluctuation, then more data would make it undeniable. The bump would grow, the significance would climb, and by summer they would know. The LHC delivered. Through the first half of 2012, the machine ran almost continuously, producing collision after collision, filling the detectors with more events than any previous accelerator in history. The two main detectors, Atlas and CMS, were recording everything they could, filtering out the junk, saving the interesting collisions, and feeding the data into the worldwide LHC computing grid for analysis. By late June, both collaborations had collected enough data that the picture was starting to come into focus. The bump at 125 giga-electron-volts was still there, and it was getting clearer. CERN scheduled a seminar for July 4, 2012. The date was not symbolic. It was not chosen to coincide with American Independence Day or any other holiday. It was chosen because the International Conference on High-Energy Physics was about to start in Melbourne, Australia, and CERN wanted to present the results before the community scattered to the other side of the planet. The timing was tight. Both Atlas and CMS were working around the clock to finalize their analyses, checking and rechecking their numbers, making sure there were no mistakes, no errors, no reasons the signal might be an artifact of the way they had processed the data. The morning of July 4th, the auditorium at CERN was packed, not just with physicists from Atlas and CMS, but with scientists from all over the world who had flown in to witness what many suspected would be the most important announcement in particle physics in decades. The press was there, cameras were set up. The atmosphere was electric in a way that scientific seminars almost never are. This was not a routine data presentation. This was the culmination of nearly 50 years of searching. The final chapter, maybe, in one of the longest hunts in the history of science. Peter Higgs was there. He was 83 years old at the time, a retired professor from the University of Edinburgh, the man who had written a 2-page paper in 1964 proposing that a field filling the universe could give particles mass and that the field should have an associated particle. He had spent nearly half a century watching other physicists search for that particle, watching experiments come up empty, watching hints appear and then dissolve. He had never expected to live long enough to see it found, but here he was, sitting in the audience, waiting. The presentations began. First, Atlas. The spokesperson walked the audience through the analysis, explaining how they had searched for the Higgs boson in multiple decay channels. The Higgs, if it existed, would not show up as a single clean signal. It would decay almost instantly into other particles, and those particles would fly outward into the detector, leaving trails and energy deposits that had to be reconstructed. Different decay channels had different signatures, and each one had to be analyzed separately. The cleanest channel, the one with the best mass resolution, was the diphoton channel. Higgs decays into 2 photons. This is a rare process. Most Higgs bosons do not decay this way. But when they do, the signal is beautiful. 2 high-energy photons flying out in opposite directions, each one deposited in the electromagnetic calorimeter with a precisely measured energy. Add up the energies, calculate the invariant mass, and you get a number. If that number clusters around 125 giga-electron-volts across many collisions, you have found something. Atlas showed the plot. A histogram with the horizontal axis showing the mass in giga-electron-volts and the vertical axis showing the number of events. Most of the plot was flat, just background noise, collisions that produced two photons, but not from a Higgs boson. But right around 125 giga-electron-volts, there was a spike, a bump. A clear, visible excess of events, sitting exactly where the December hint had suggested something might be. The second major channel was 4-lepton. This is what happens when a Higgs boson decays into two Z bosons, and each Z boson immediately decays into a pair of leptons, electrons or muons. This channel is even rarer than diphoton, but it is also very clean. 4 leptons flying out of a single collision, each one leaving a clear track in the detector. Measure their energies and angles, reconstruct the invariant mass, and again you get a number. And again, Atlas showed a plot, another bump, right around 125 giga-electron-volts. There were other channels too. Higgs decaying into W boson pairs, into tau-lepton pairs, into bottom quark pairs. Not all of them showed clear signals. Some were too swamped by background noise, but the diphoton and 4-lepton channels were enough. Combined, they pointed to the same mass, the same particle. And when Atlas combined all their data, all their channels, all their statistical methods, they arrived at a single number, a local significance of 5 sigma. 5 sigma. That is the threshold. That is the standard particle physics uses to claim a discovery. 5 sigma means there is only about a 1 in 3.5 million chance that the signal you are seeing is a random fluctuation. It is not proof in the absolute sense. Nothing in experimental science ever is. But it is close enough that the community agrees to call it a discovery. Atlas had crossed that line. They had found a new particle. Mass around 126 giga-electron-volts. Properties consistent with the standard model Higgs boson. Then it was CMS's turn. The second detector, the independent collaboration. The group that had been analyzing the same collisions from the same machine, but using different software, different techniques, different people. If CMS saw the same thing Atlas saw, the discovery would be rock solid. If CMS saw nothing or saw something different, the whole thing would be thrown into doubt. CMS presented, same structure, multiple decay channels, same careful analysis, and the result was almost identical. CMS reported a new particle at 125.3 giga-electron-volts, give or take 0.6. The diphoton channel showed a clear excess. The 4-lepton channel showed a clear excess. The combined significance was 5.0 sigma, right at the threshold, right where it needed to be. The two detectors, built by different teams, analyzed by different collaborations, had independently arrived at the same conclusion. There was a new particle. It was sitting at 125 giga-electron-volts, and its properties, as far as anyone could tell from the data available, were exactly what you would expect if it was the Higgs boson. The room erupted. Not polite academic applause, thunderous applause. People standing, cheering. Physicists are not generally an emotional group. Scientific seminars do not usually involve standing ovations, but this was not a usual seminar. This was the end of a 50-year search, the confirmation of a theory that had been proposed before most of the people in the room were born, the discovery of the last missing piece of the standard model, the particle that explains why anything has mass. Peter Higgs was crying. He did not try to hide it. Cameras caught the moment. An elderly man, visibly emotional, wiping his eyes as the auditorium applauded around him. Later, when reporters asked him how he felt, he said he never expected it to happen in his lifetime. He had written the paper in 1964, been ignored for years, watched the idea slowly gain acceptance, and then spent decades waiting for someone to prove it was real. Now, at 83, he had finally seen it, the particle that bore his name, confirmed. François Englert was there too. He and Robert Brute had written one of the other papers in 1964, proposing the same mechanism. Brute had died in 2011, just a year before the discovery, never knowing whether his work would be vindicated. Englert, like Higgs, was emotional. The two of them had spent their careers on this idea, and now, nearly 50 years later, it had been proven correct. The announcement made headlines around the world. Not just in scientific journals, mainstream news, front pages. The discovery of the Higgs boson was treated as a major event, the kind of thing that transcends academia and becomes part of the broader cultural conversation. People who had never heard of particle physics were suddenly talking about the God particle, a nickname Higgs himself hated, but which had stuck in the popular imagination. The discovery was framed as a triumph of human ingenuity. Thousands of scientists from dozens of countries working together for decades, building the most complex machine ever constructed, and using it to answer one of the deepest questions in physics. But the scientists themselves were more cautious. The July 4th announcement was not the end of the story. It was the beginning of a new chapter. Yes, Atlas and CMS had found a new particle. Yes, the mass and the decay channels were consistent with the standard model Higgs boson. But consistent with is not the same as proven to be. The standard model makes very specific predictions about the Higgs boson. It predicts not just the mass, but the spin, the parity, the decay rates into different channels, the production cross-section, all of it. The July 4th data was enough to claim a discovery, but it was not enough to confirm every detail. The particle they had found was definitely a boson. That much was clear from the decay into two photons. Photons have spin 1, and the rules of quantum mechanics allow two spin 1 particles to combine only into a boson with integer spin, so the new particle was a boson. But was it spin 0, like the Higgs, or spin 2, like a graviton? The data leaned towards spin 0, but more measurements were needed to rule out the alternatives. The decay rates also needed to be checked. The standard model predicts how often a Higgs boson should decay into each channel. Diphoton, 4-lepton, tau pairs, bottom quarks, W bosons, all of them have predicted branching ratios. If the particle Atlas and CMS had found was really the Higgs, then the measured rates should match the predictions. Early data suggested they did. CMS reported that the production rate, the number of Higgs bosons produced per collision, was consistent with the standard model prediction. The ratio of observed events to expected events was about 0.8, give or take 0.22. That is close enough to 1 that you can say the data fits, but it is not exact. There was room for deviation. Room for the possibility that this particle, while Higgs-like, might not be exactly the Higgs the standard model predicted. Over the next several months, both collaborations continued analyzing their data, refining their measurements, checking every detail. By early 2013, the picture had sharpened. The particle was definitely spin 0. The decay rates matched the standard model predictions across all channels. The couplings to other particles, which should be proportional to their masses if the Higgs mechanism is correct, were exactly what the theory predicted. The top quark, the heaviest particle in the standard model, coupled strongly to the Higgs. The bottom quark, lighter than the top, but still heavy by particle standards, coupled less strongly, but still significantly. The W and Z bosons, which get their masses directly from the Higgs mechanism, coupled exactly as expected. Every test came back consistent with the standard model Higgs boson. Not just close, not just in the ballpark, exact, within the precision of the measurements. The particle was not just Higgs-like, it was the Higgs. The field was real, the mechanism worked. Mass, the thing that gives matter its inertia, that allows particles to slow down and bind together and form atoms and molecules and everything else, came from an invisible field filling the universe. And that field, when you disturbed it with enough energy, produced a particle that weighed 125 giga-electron-volts and lasted for less than a trillionth of a second before decaying into a spray of other particles. The Nobel Prize came the following year, October 2013. The Royal Swedish Academy of Sciences announced that the prize in physics would be awarded to Peter Higgs and Francois Englert for the theoretical discovery of a mechanism that contributes to our understanding of the origin of mass of subatomic particles, not for discovering the particle, for the theory. The prize recognized that the experimental discovery, as monumental as it was, rested on a foundation of theoretical work that had been done nearly 50 years earlier. Higgs and Englert had predicted the particle before anyone knew how to build a machine capable of finding it. They had written down the equations, worked out the implications, and then waited half a century for the technology to catch up. Robert Brute, who had co-authored the paper with Englert, was not included in the prize because he had died in 2011. The Nobel Prize is not awarded posthumously. Gerald Guralnick, Carl Hagen, and Tom Kibble, who had also worked on the mechanism in 1964, were not included either. The prize can only be shared by 3 people, and the committee decided Higgs and Englert were the ones whose work had been most directly validated by the LHC discovery. This caused some controversy. Science is collaborative. The Higgs mechanism was not the work of one person or even 2. It was the result of multiple groups arriving at the same idea independently. But the Nobel Prize, by its rules, can only recognize a limited number of people. Higgs and Englert got the medal, the others got footnotes. For the broader physics community, the discovery was vindication. The Standard Model, which had been under construction since the 1960s, was finally complete. Every particle it predicted had been found. Every force it described had been tested. Every prediction it made had been confirmed, often to absurd levels of precision. The model explained how quarks bind together to form protons and neutrons. It explained how the weak force causes certain particles to decay. It explained how photons mediate the electromagnetic force. It explained how gluons hold the nucleus together. And now, with the Higgs boson confirmed, it explained how particles acquire mass. This was not a small achievement. The Standard Model is arguably the most successful scientific theory ever constructed. It describes the behavior of matter and energy at the smallest scales with a level of accuracy that borders on the uncanny. Predictions made by the Standard Model have been tested in thousands of experiments over more than 50 years, and the theory has passed every test. There are phenomena it does not explain. Dark matter, for example. The Standard Model has no candidate particle for dark matter. Gravity is not part of the Standard Model. The model says nothing about why the universe contains more matter than antimatter, or why the cosmological constant has the value it does. But within its domain, within the realm of particle physics and the forces that govern subatomic interactions, the Standard Model is as close to a complete description of reality as science has ever produced. And the Higgs boson was the keystone. Without it, the whole structure would have collapsed. The equations that describe the weak force and electromagnetism only work if particles acquire mass through the Higgs mechanism. Take the Higgs away, and the theory falls apart. The discovery in 2012 was not just finding a new particle. It was confirming that the foundation of the Standard Model was solid. That the framework physicists had been building for 50 years was not just a useful approximation, but a genuine reflection of how the universe works at the deepest level we can currently probe. But even as the champagne was being opened and the Nobel speeches were being written, physicists were already looking ahead, because the Standard Model, for all its successes, is not the final theory. It cannot be. It leaves too many questions unanswered. Why do particles have the masses they do? The Higgs mechanism explains that particles acquire mass by interacting with the Higgs field, but it does not explain why the interaction strengths are what they are. The top quark couples strongly to the Higgs. The electron couples weakly. Why? The Standard Model has no answer. Those coupling strengths, called Yukawa couplings, are free parameters. You have to measure them experimentally and plug them into the theory by hand. The model does not predict them. Then there is the mass of the Higgs itself, 125 giga-electron volts. That number is a problem, not because it is wrong, but because it is inexplicably small. Quantum mechanics predicts that the Higgs boson's mass should receive enormous contributions from virtual particles popping in and out of the vacuum. Every particle that couples to the Higgs, every force that interacts with it, should add to its mass. When you add up all those contributions, the Higgs should weigh something like 10 to the power of 19 giga-electron volts. That is a 1 followed by 19 zeros. A mass so large, it is near the Planck scale, where quantum mechanics and gravity become equally important, and the entire framework of particle physics breaks down. The fact that the Higgs weighs 125 giga-electron volts instead of 10 to the 19th means something is cancelling out all those huge contributions. Something is fine-tuning the mass to an absurdly precise degree. The Standard Model has no explanation for this. It is called the hierarchy problem, and it is one of the biggest unsolved puzzles in particle physics. There is also the question of whether the Higgs boson is fundamental. The Standard Model treats it as a point particle, a single indivisible quantum of the Higgs field. But what if it is not? What if the Higgs boson is composite, made of smaller constituents bound together by some new force we have not discovered yet? That would explain why its mass is so much lighter than the Planck scale. Composite particles, like protons, have masses determined by the dynamics of whatever binds their constituents together, not by the fundamental mass scale of the theory. If the Higgs is composite, then the Standard Model is not the final story. There is something deeper underneath. The measurements made at the LHC since 2012 have been looking for hints of that deeper structure. Every time the Higgs decays, every time it is produced in a collision, physicists measure the rates and compare them to what the Standard Model predicts. So far, every measurement has come back consistent with the Standard Model. The Higgs behaves exactly like a fundamental scalar boson, not like something with internal structure. But the precision of the measurements is limited. There is still room for small deviations. Room for the possibility that the Higgs is not quite what the Standard Model says it is. And then there is the question of what else might be out there. The Higgs boson was the last missing particle in the Standard Model. But the Standard Model is not a theory of everything. It does not include gravity. It does not explain dark matter or dark energy. It does not explain why the universe is made of matter instead of antimatter. If there are new particles beyond the Standard Model, particles that could answer those questions, the LHC is the machine most likely to find them. And the Higgs might be the key. If there is new physics hiding just beyond the energy scales the LHC can reach, the Higgs might couple to it. New particles might decay into the Higgs. The Higgs might decay into new particles. Measuring the Higgs precisely could reveal subtle hints of those interactions, breadcrumbs pointing the way to the next breakthrough. The discovery in 2012 was the end of one story. The 50-year search for the Higgs boson was over. The particle had been found, the field was real. The mechanism worked, but it was also the beginning of a new story, because finding the Higgs did not answer all the questions. It opened new ones. Why does the Higgs have the mass it does? Why do particles couple to it with the strengths they do? Is the Higgs fundamental or composite? Are there other Higgs bosons, heavier ones we have not found yet? And what lies beyond the standard model, in the energy ranges we have not yet been able to probe? The LHC had delivered the particle physics community had been chasing for half a century. Now the question was what to do with it. The champagne had barely gone flat when the question started. July 2012, CERN, the auditorium still buzzing with the announcement that would make front pages around the world. The Higgs boson had been found. The standard model was complete. 50 years of theoretical predictions, decades of experimental hunting, billions of dollars, thousands of scientists, and finally, confirmation. The particle was real. The field was real. Mass had an explanation. Victory. Except physicists do not do victory laps. Or rather, they do, but the lap takes about 15 minutes, and then someone in the back of the room raises their hand and asks the question that ruins everything. In this case, the question was simple. Okay, we found the Higgs, now what? Because here is the thing about the standard model. It is stunningly successful. It describes the behavior of particles and forces at the smallest scales with a precision that borders on the absurd. Predictions made 50 years ago have been confirmed to 14 decimal places. The model predicted the existence of particles that were later discovered exactly where and when the model said they should be. The W boson, the Z boson, the top quark, the tau neutrino, every single one of them showed up on schedule. The Higgs was the last piece, the final missing particle, the one prediction that had been hanging in the air since 1964. And when it was found, it had exactly the properties the model predicted. The mass was in the expected range, the decay channels matched, the coupling strengths were correct. The standard model had passed its final exam with honors. And yet, the standard model is not a theory of everything. It is not even close. It is a theory of some things, very important things, yes, but nowhere near everything. It describes 3 of the 4 fundamental forces: electromagnetism, the weak nuclear force, the strong nuclear force. It ignores gravity entirely, not because gravity is unimportant. Gravity is the reason planets orbit stars and the reason you do not float off into space. But at the scales the standard model operates, the subatomic realm where particles are measured in femtometers and energies in giga-electron-volts, gravity is so weak it might as well not exist. A single magnet on your refrigerator overpowers the gravitational pull of the entire Earth when it holds up a shopping list. Gravity matters at large scales, planetary scales, cosmological scales. The standard model does not care about large scales, so gravity got left out. That is problem 1. The standard model is silent on the force that shapes the structure of the universe. Problem 2 is dark matter. About 85% of the matter in the universe does not interact with light. It does not emit photons. It does not absorb them. It does not reflect them. We know it is there because we can see its gravitational effects. Galaxies rotate too fast to be held together by the visible matter alone. Galaxy clusters are heavier than the sum of their stars and gas. The universe's large-scale structure, the way galaxies are distributed across billions of light years, only makes sense if there is 5 times more matter out there than we can see. That matter is dark. Not dark because it is far away or hidden behind something. Dark, because it does not interact with electromagnetic radiation at all. The Standard Model has no candidate for dark matter, not one. Every particle in the Standard Model interacts with light in some way, either directly like electrons and quarks, or indirectly through other particles. If dark matter is real, and every observation suggests it is, then it is made of something the Standard Model does not include. Something new, something we have not discovered yet. Problem 3 is dark energy. About 68% of the total energy in the universe is not matter at all. It is something else, something that behaves like a cosmological constant, a kind of energy embedded in the fabric of space itself. Dark energy is causing the expansion of the universe to accelerate. Galaxies are not just moving away from each other, they are moving away faster and faster. This was discovered in 1998, and it was so unexpected that the scientists who found it spent months checking their data, convinced they had made a mistake. They had not. The acceleration is real, and the Standard Model has nothing to say about it. Dark energy is not a particle. It is not a force in the traditional sense. It is a property of space. And the Standard Model, which is a theory of particles and forces, does not include properties of space. Problem 4 is antimatter. The universe, as far as we can tell, is made almost entirely of matter. Protons, neutrons, electrons, the stuff that makes up stars and planets and people. But the Standard Model predicts that when the universe was born, matter and antimatter should have been created in equal amounts. Every particle should have had an antiparticle partner, and when matter meets antimatter, they annihilate, turning into pure energy. If the universe started with equal parts matter and antimatter, they should have destroyed each other completely, leaving nothing but a sea of photons, no atoms. No stars, no us. But here we are, which means something somewhere broke the symmetry between matter and antimatter. The Standard Model allows for some asymmetry, but not nearly enough to explain why the universe is made of matter instead of radiation. There is a missing ingredient, a process we do not understand. So yes, the Standard Model is complete in the sense that every particle it predicts has been found. But it is incomplete in the sense that it leaves enormous questions unanswered. Questions about gravity, about dark matter, about dark energy, about the imbalance between matter and antimatter. The discovery of the Higgs boson did not resolve any of those questions. It confirmed that the mechanism the Standard Model uses to give particles mass is correct. But it did not explain why the universe is the way it is at the largest scales. It did not explain what most of the universe is made of. It did not explain why anything exists at all. And then there is the Higgs itself, the particle that was supposed to complete the model. Because the moment physicists had a precise measurement of its mass, 125 giga-electron-volts, they realized something deeply uncomfortable. That mass is a problem, not because it is wrong. The mass is exactly what the experiments measured. The problem is that it is far too light. According to the rules of quantum mechanics, it should be much, much heavier. And the fact that it is not suggests that either the universe is engaged in an extraordinarily precise balancing act, or there is new physics hiding just out of reach. This is called the naturalness problem, and it goes like this. In quantum field theory, particles do not just sit there quietly. They are constantly being buffeted by the vacuum, by virtual particles popping in and out of existence. These are not real particles in the sense that you can catch them or measure them directly. They are fluctuations in the fields that fill space, brief disturbances that appear and vanish on timescales so short they do not violate the laws of physics. Virtual particles are everywhere. They contribute to the properties of real particles, shifting their masses and interaction strengths in ways that can be calculated. For most particles, these shifts are small, but for the Higgs boson, they are enormous. Every particle that couples to the Higgs, every force that interacts with it, contributes a quantum correction to its mass. The top quark, which couples very strongly to the Higgs, adds a huge correction. Virtual top quarks pop in and out of the vacuum, interact with the Higgs field, and shift the Higgs mass upward. The W and Z bosons do the same. So do all the other quarks and leptons. When you add up all these contributions, the Higgs mass should be something like 10 to the power of 19 giga-electron-volts. That is a 10 followed by 19 zeros, a mass so stupendously large that it is up near the Planck scale, the energy where quantum mechanics and gravity become equally important and space-time itself starts to behave in ways we do not understand. But the Higgs boson does not weigh 10 to the 19th giga-electron-volts. It weighs 125. That is 17 orders of magnitude lighter. 17. The only way this works is if there is another set of contributions, things we have not discovered yet, that cancel out almost all of the huge quantum corrections, leaving behind the small measured mass. The cancellation has to be precise to about 1 part in 10 to the 17th. That is like balancing a pencil on its point, not on a table, but on the tip of a needle in a hurricane for billions of years. This kind of fine-tuning makes physicists deeply uncomfortable. Not because it is impossible. The universe is what it is, and if the numbers happen to be fine-tuned, that is just how it turned out. But fine-tuning is unsatisfying. It feels like cheating. Theories that require you to dial in parameters to 16 or 17 decimal places to make them work are not wrong, but they are suspicious. They suggest you are missing something, some deeper principle, some underlying structure that explains why the numbers are what they are without needing to adjust them by hand. The naturalness problem is the biggest hint we have that the standard model is not the final story. There is something else. Some new physics, some new particles or forces or symmetries that stabilize the Higgs mass and explain why it is so much lighter than it should be. And one of the most popular candidates for that new physics is called supersymmetry. Supersymmetry, SUSY for short, is a proposed extension of the standard model that doubles the number of particles. For every fermion, every matter particle like quarks and leptons, SUSY predicts a superpartner that is a boson. For every boson, every force-carrying particle like photons and gluons, SUSY predicts a superpartner that is a fermion. None of these superpartners have been discovered, not one. But if they exist, they would solve the naturalness problem. The quantum corrections from superpartners would be opposite in sign to the corrections from ordinary particles. The contributions from virtual top quarks and virtual stop quarks, the supersymmetric partner of the top, would cancel each other out almost exactly. The Higgs mass would be light, not because of fine-tuning, but because of symmetry. A fundamental principle of nature that keeps everything balanced. SUSY is not just a patch to fix the Higgs mass. It has other virtues. It predicts a natural candidate for dark matter. The lightest supersymmetric particle, if it is stable, would not interact with light and would not decay into anything lighter. It would be invisible, weakly interacting. Exactly what dark matter needs to be. SUSY also plays nicely with attempts to unify the forces. The strong, weak, and electromagnetic forces have different strengths at the energies we can currently probe. But if you extrapolate those strengths to higher energies, they almost converge to a single value, the kind of convergence you would expect if all three forces are different manifestations of a single unified force. Almost, but not quite. If you add the superpartners predicted by Susie, the forces converge exactly. Susie makes the math prettier, it makes the theory more elegant, and it solves real problems. The catch is that no one has found any evidence for it. The LHC, which was expected to discover superpartners if they existed in the mass range below a few tera-electron volts, has seen nothing. No squarks, no leptons, no gluinos, no neutralinos. The searches have been exhaustive. Multiple decay channels, multiple production mechanisms, every possible signature analyzed, and every search has come up empty. Susie is not ruled out. The superpartners could be heavier than the LHC can reach. But the longer the LHC runs without finding them, the less natural Susie starts to look. If the superpartners are very heavy, then Susie does not solve the naturalness problem anymore. You end up needing fine-tuning again, just at a different level. This has left the field in an awkward place. The standard model fits all the data. The Higgs boson behaves exactly as predicted. But the theory feels incomplete. The naturalness problem suggests there should be new physics at the energy scales the LHC is probing. Susie is the leading candidate for what that new physics might be, but the LHC has not found it. So either the superpartners are heavier than expected, or Susie is not the answer, or naturalness is not a reliable guide, or the universe really is fine-tuned and there is no deeper explanation. That ambiguity is frustrating, but it is also exciting, because the discovery of the Higgs boson did not close the book on particle physics. It opened a new chapter. The Higgs is not just the final piece of the standard model. It is a tool, a probe, a window into whatever lies beyond. The reason is simple. The Higgs interacts with other particles. That is its job. It couples to quarks and leptons, giving them mass. It couples to the W and Z bosons, giving them mass. If there are new particles out there, particles beyond the standard model, they might couple to the Higgs too, and if they do, their effects would show up in the way the Higgs behaves. The Higgs could decay into new particles. New particles could decay into the Higgs. The production rate for Higgs bosons could be higher or lower than the standard model predicts if new particles are contributing to the process. This is why physicists are now measuring the Higgs with obsessive precision. Every decay channel, every production mechanism, every tiny detail of how the Higgs is created and how it falls apart is being studied. The goal is to find deviations, small differences between what the standard model predicts and what the experiments measure. A decay rate that is slightly higher than expected, a coupling strength that is slightly off. Anything that does not fit perfectly could be a clue, a hint that something new is interacting with the Higgs in ways the standard model does not account for. So far, every measurement has come back consistent with the standard model. The Higgs couples to the top quark with the predicted strength. It couples to the W and Z bosons with the predicted strength. It decays into bottom quarks, tau leptons, photons, all at the predicted rates. The agreement is so good it is almost eerie, but the measurements are not infinitely precise. There is still room for small deviations, effects at the few percent level that the current data cannot resolve. As the LHC continues to run, as more collisions are recorded and analyzed, those uncertainties will shrink, and if there is new physics hiding in the Higgs couplings, it will eventually show up. One particularly tantalizing possibility is that the Higgs could be a portal to dark matter. If dark matter particles exist, and if they are light enough, the Higgs boson could decay into them. The decay would be invisible. Dark matter does not interact with the detectors. It would just fly out of the collision without leaving a trace, but you could still detect it indirectly. If a Higgs boson is produced in a collision and then decays invisibly, the total energy and momentum of the visible particles flying out would not add up. There would be missing energy, a sign that something unseen had carried part of the energy away. The standard model predicts a small amount of invisible Higgs decay, about 0.1%, from decays into neutrinos. But if the rate is higher than that, it could be a signal of dark matter. The current measurements put an upper limit on the invisible decay rate at about 10%. That is not a detection, it is a constraint. If the Higgs does decay into dark matter, it is not doing so very often. But 10% is a lot of room. If future measurements show even a few percent of Higgs decays going invisible, that would be a revolution. It would mean dark matter is not some exotic substance that only interacts gravitationally. It would mean dark matter couples to the Higgs field, meaning it has mass in the same way ordinary matter does, meaning it is connected to the standard model through the one particle that gives everything else its mass. Another possibility is that the Higgs boson we found is not the only one. The standard model predicts one Higgs boson, but extensions of the standard model, theories that try to solve the problems the standard model leaves unanswered, often predict more. Supersymmetry, for example, predicts 5 Higgs bosons, 3 neutral ones, and 2 charged ones. The one we found at 125 giga-electron-volts would be the lightest. The others would be heavier, possibly much heavier, sitting in a mass range the LHC has not fully explored yet. If there are multiple Higgs bosons, they would interact with each other, they would mix. The lightest one, the one we have already found, would have properties that depend on the existence of the heavier ones. Measuring those properties precisely could reveal hints of the others, even if they are too heavy to produce directly. This is one reason why the precision measurements of the known Higgs are so important. Every coupling strength, every branching ratio, every tiny deviation from the standard model prediction is a potential clue pointing toward new particles we have not seen yet. The Higgs might also interact with particles that have nothing to do with mass. There are theories where the Higgs couples to a hidden sector, a whole set of particles and forces that exist alongside the standard model but do not interact with ordinary matter except through the Higgs field. These hidden particles would not show up in normal collisions, they would not leave tracks in the detectors, but they could be produced when a Higgs boson decays, and their effects could be inferred from missing energy or unusual decay patterns. All of this is speculative. None of it has been confirmed. But the fact that these possibilities exist, that the Higgs could be the key to unlocking new physics, is why the particle's discovery did not end the conversation. It started a new one. The question is no longer whether the Higgs exists. The question is what the Higgs can tell us about the parts of the universe the standard model does not explain. There is another uncomfortable possibility. Maybe the standard model is it. Maybe there is no new physics at the energy scales the LHC can reach. Maybe the superpartners are too heavy. Maybe dark matter does not interact with the Higgs. Maybe the naturalness problem is not a real problem, just an aesthetic preference, and the universe is fine-tuned for reasons we do not understand and maybe never will. If that is the case, then the LHC will keep running, keep collecting data, and keep confirming the standard model to higher and higher precision. That would be scientifically valuable. Precision measurements matter. But it would also be deeply unsatisfying. Physicists did not build the most complex machine in human history just to confirm what they already knew. They built it to find something new. The good news is that the search is not over. The LHC is scheduled to run through the 2030s, possibly into the 2040s. Upgrades are planned that will increase the collision rate, allowing the detectors to collect even more data. Future colliders are being designed. A proposed machine called the Future Circular Collider, FCC, would be 100 kilometers in circumference, nearly 4 times the size of the LHC, and capable of reaching collision energies of 100 tera-electron volts. That is 7 times higher than the LHC. If there is new physics hiding just above the energy range the LHC can reach, the FCC would find it. But building the FCC would take decades and cost tens of billions of dollars, and there is no guarantee it would find anything. The history of particle physics over the last 50 years is a history of machines that were built to discover new particles, and sometimes did, and sometimes did not. The LHC found the Higgs. That was a triumph. But it has not found anything else. No superpartners, no extra dimensions, no dark matter particles, just the standard model, confirmed over and over again with increasing precision. At some point, the question becomes whether it is worth continuing to build bigger and bigger machines to search for particles that might not exist, or whether the money and effort would be better spent on other kinds of experiments. Astrophysical observations, neutrino detectors, gravitational wave observatories, searches for dark matter that do not rely on colliders. The debate over what comes after the LHC is one of the most important conversations happening in physics right now, because the discovery of the Higgs boson, while historic, did not answer the big questions. It answered one question, a very important question, yes, but one question. The universe is still mostly dark matter and dark energy. Gravity is still not part of the standard model. The imbalance between matter and antimatter is still unexplained. And the Higgs boson, sitting at 125 giga-electron volts, is still far lighter than quantum mechanics says it should be. The standard model is complete. Every particle predicted has been found. The Higgs boson sits at the top of the achievement list, confirmed, measured, tested, and verified to a precision that would have seemed impossible 50 years ago. The field is real. The mechanism works. Mass has an explanation. Case closed. Except there is a question that keeps resurfacing, quietly, in the back of conference rooms and in the footnotes of technical papers. A question that most physicists would prefer not to think about too hard, because the answer, if it goes the wrong way, unravels everything. The question is this: is the Higgs boson actually fundamental, or is it made of something smaller? That might sound like a technicality, a detail for specialists to argue about in journals that no one outside the field will ever read. It is not. If the Higgs boson is not a fundamental particle, if it has internal structure, if it is composite, then the standard model is not the end of the story. It is not even close. It is a placeholder, a useful approximation that works at the energy scales we can currently probe, but breaks down when you look closer. And everything we think we understand about mass, about the Higgs field, about why particles have the properties they do, would need to be rewritten. The idea that particles can have internal structure is not new. It is not even controversial. We have known for more than a century that atoms are not fundamental. They are made of protons, neutrons, and electrons. By the 1960s, we knew protons and neutrons were not fundamental either. They are made of quarks, bound together by gluons, the particles that carry the strong nuclear force. Quarks, as far as we can tell, are fundamental, point particles with no internal structure. But we thought protons were fundamental too, until we looked closer and realized they were not. So the question is reasonable. Have we looked closely enough at the Higgs? The standard model treats the Higgs boson as a fundamental scalar particle. Scalar means it has no spin in the way particles like electrons do. It is just a point, a ripple in the Higgs field with no internal parts and no substructure. This is convenient because it makes the math work. A fundamental Higgs fits cleanly into the equations that describe how particles acquire mass, but convenient is not the same as correct. The universe does not care whether our theories are convenient, it cares whether they match reality. And there are reasons, good reasons, to suspect the Higgs might not be as simple as the Standard Model assumes. The first reason is the mass. Again, the Higgs boson weighs 125 giga-electron-volts. That number is a problem because quantum mechanics says it should not be that light. Virtual particles, fluctuations in the fields that fill space, should be adding enormous corrections to the Higgs mass. Top quarks, W bosons, every particle that couples to the Higgs contributes a quantum correction that pushes the mass upward. When you add up all those contributions, the Higgs should weigh something close to the Planck scale, 10 to the 19th giga-electron-volts. It does not. It weighs 125. The only way that works is if something else is cancelling out almost all of the huge corrections, leaving behind the small measured mass. That something could be supersymmetry, new particles whose contributions cancel the Standard Model corrections, but no one has found any evidence for supersymmetry. The LHC has been searching for more than a decade, and the superpartners have not shown up. Another possibility, one that is taken seriously by a subset of the theoretical community, is that the Higgs is composite. If the Higgs boson is not a point particle, but is instead made of smaller constituents bound together by some new force, then its mass is not determined by quantum corrections from virtual particles. It is determined by the dynamics of whatever is holding the constituents together. Composite particles, like protons, have masses that come from the binding energy of their internal parts, not from fundamental mass parameters. If the Higgs is composite, the naturalness problem goes away. The mass is light because the binding energy is relatively low, no fine-tuning required, no cancellations needed. This idea has a name, Technicolor. It is not a new idea. The first Technicolor models were proposed in the late 1970s, before the Higgs boson was discovered, as an alternative to the Higgs mechanism. The idea was that instead of a fundamental scalar field giving particles mass, a new strong force, analogous to the force that binds quarks into protons, would bind new particles called techniquarks into composite states. Those composite states would play the role the Higgs plays in the Standard Model. They would give mass to the W and Z bosons. They would couple to other particles, but they would not be fundamental. They would be bundles of smaller things, held together by a force that operates at energy scales just beyond what we can currently reach. Technicolor fell out of favor for a while because early versions of the theory made predictions that did not match the data. The composite particles were too heavy, the couplings did not work out. The precision measurements of the W and Z boson masses, which had been made to exquisite accuracy at LEP, ruled out many of the simple Technicolor models. But the discovery of the Higgs boson at 125 giga-electron-volts changed the conversation. A particle that light, sitting right in the mass range where composite models could naturally produce a bound state, reopened the possibility. Modern versions of Technicolor, sometimes called composite Higgs models, are more sophisticated than the original proposals. They predict a Higgs-like particle that behaves almost exactly like the Standard Model Higgs at the energies we have probed so far, but would reveal its composite nature if you could look closely enough. The experimental challenge is that looking closely enough is extraordinarily difficult. The Higgs boson has a lifetime of about 10 to the power of -22 seconds. That is a decimal point, followed by 21 zeros, and then a 1. In that time, the Higgs does not travel any measurable distance. It does not exist long enough for its internal structure, if it has any, to manifest in an obvious way. You cannot open up a Higgs boson and look inside. You cannot scatter other particles off it and measure how the scattering pattern changes at different angles, the way physicists did with protons in the 1960s to discover quarks. The Higgs appears and decays before you can do anything with it. What you can do is measure how it behaves, how often it is produced, how it couples to other particles, how often it decays into different channels. If the Higgs is composite, those measurements should eventually deviate from the standard model predictions, not by a lot. The deviations would be small, a few percent at most, because whatever structure the Higgs has is being held together at energy scales we cannot quite reach yet. But small deviations are detectable if you have enough data and if your measurements are precise enough. This is why the LHC collaborations are now focusing on precision. Every Higgs boson produced is an opportunity to test whether it really is a point particle or whether there is something more going on underneath. One of the cleanest tests involves the Higgs coupling to photons. In the standard model, the Higgs does not couple directly to photons. It has no electric charge. But the Higgs can decay into two photons through a process where it briefly turns into a virtual top quark, or a virtual W boson, and those virtual particles then emit the photons. This is called a loop process because the Feynman diagrams that describe it have loops in them. If the Higgs is composite, the loop contributions could be different. New particles, the constituents of the Higgs, could show up in the loops and change the decay rate. If the measured rate of Higgs decays into two photons is even a few percent higher or lower than the standard model predicts, that could be a sign of compositeness. So far, the measurements are consistent with the standard model. The diphoton decay rate matches the prediction within the uncertainties. But the uncertainties are still a few percent. There is room for small deviations. As the LHC continues to collect data, those uncertainties will shrink. If the decay rate stays exactly where the standard model says it should, that is evidence the Higgs is fundamental. If it shifts, even slightly, that is evidence of new physics, new particles, new forces, a deeper layer of reality. Another test involves the Higgs self-coupling. This is the rate at which Higgs bosons interact with each other. In the standard model, the Higgs field has a potential, a mathematical function that describes how the field behaves when it is disturbed. The shape of that potential determines the mass of the Higgs boson and also determines how strongly two Higgs bosons couple to each other. If you could produce a pair of Higgs bosons in a single collision, you could measure that coupling directly. If the Higgs is composite, the self-coupling could be different from what the standard model predicts. The binding dynamics of the constituents would change the shape of the potential, which would change the coupling. Producing Higgs pairs is rare, far rarer than producing a single Higgs. The LHC has been searching for Higgs pair production since the particle was discovered, and so far no definitive signal has been found. The current data allows only an upper limit on how often it happens, but the limit is coming down. With more collisions, with better analysis techniques, with detectors that can separate signal from background more effectively, Higgs pair production will eventually be observed. And when it is, the measurement of the self-coupling will be one of the most important tests of whether the Higgs is fundamental or composite. There is also the possibility that the Higgs couples to particles we have not discovered yet. In composite models, the constituents of the Higgs, whatever they are, would be new particles. They might be heavy, too heavy to produce directly at the LHC, but they could still affect the properties of the Higgs through virtual processes. Think of it like this. If the Higgs is made of technequarks, those technequarks are bound together by a new force. That force has its own force carriers, particles analogous to gluons. Those force carriers could appear as virtual particles in Higgs decays, shifting the rates in subtle ways. Detecting those shifts would not tell you exactly what the constituents are, but it would tell you they are there, that the Higgs is not fundamental, that there is another layer below. The philosophical implications of this are unsettling. For more than a century, the story of physics has been a story of peeling back layers. Atoms were thought to be indivisible. They were not. They were made of protons, neutrons, and electrons. Protons and neutrons were thought to be fundamental. They were not. They were made of quarks. Quarks are thought to be fundamental. Are they? We have no evidence to suggest they are not, but we also had no evidence protons were composite until we built machines powerful enough to look inside them. The question is whether this process ever ends. Is there a bottom? A final layer where particles are truly indivisible, with no internal structure, no constituents, just fundamental entities that cannot be broken down any further? Or does it go on forever, an infinite regress, where every time you look closer you find another layer and another and another, with no end in sight? The standard model assumes there is a bottom. Quarks, leptons, the W and Z bosons, the photon, the gluon, the Higgs, those are the fundamental particles, nothing smaller. But that assumption is not based on some deep principle. It is based on the fact that we have not seen any evidence of substructure yet. The word yet is doing a lot of work there. We have not seen evidence of substructure at the energy scales we can currently probe. But every time we have built a more powerful microscope, every time we have pushed to higher energies and shorter distances, we have found new layers. Atoms had nuclei. Nuclei had protons and neutrons. Protons and neutrons had quarks. Why should it stop there? Why should the Higgs, or quarks, or any of the so-called fundamental particles be truly fundamental? If the Higgs is composite, it raises the question of whether the other particles are composite too. Maybe quarks are made of something smaller, prions, some theories call them, subquarks, constituents of constituents. If that is the case, then the standard model is not a theory of fundamental particles. It is a theory of effective particles, objects that look point-like at the energies we can reach but reveal their structure when you push to higher energies. This is not a fringe idea. Composite models of quarks and leptons have been proposed and studied for decades. None of them have been confirmed, but none of them have been ruled out either. The problem is that testing them requires energies far beyond what the LHC can deliver. You would need a collider many times more powerful, or a completely different experimental approach. Something that does not rely on smashing particles together, but probes their structure in some other way. One possibility is to look for contact interactions. These are deviations in scattering processes that would show up if particles have internal structure. When two particles collide, the way they scatter depends on the forces acting between them and on whether the particles are point-like or extended. If quarks are composite, then at very high energies, when the collision is violent enough to probe the internal structure, the scattering pattern would change. It would deviate from what you expect for point particles. The same logic applies to the Higgs. If it is composite, collisions involving the Higgs should show deviations at high enough energies. The challenge is reaching those energies. The LHC is not there yet, and it might never be. Another approach is to look for excited states. If the Higgs is composite, made of constituents bound together by some new force, then just like atoms have excited states where the electrons sit in higher energy levels, the Higgs could have excited states where the constituents are bound in higher energy configurations. Those excited states would be heavier versions of the Higgs, particles with the same quantum numbers but higher masses. If you could produce them, they would decay back into lighter particles, possibly including the standard Higgs boson, and their existence would be proof that the Higgs has internal structure. The problem is that excited states, if they exist, are likely to be heavy, heavier than what the LHC can reach. You would need a next-generation collider to produce them. The proposed future circular collider, with collision energies 7 times higher than the LHC, might be able to do it. But that machine will not be built for decades, if it gets built at all. And even if it is built, there is no guarantee it will find anything. The excited states could be even heavier than the FCC can reach. Or they might not exist at all if the Higgs is fundamental after all. This is the frustrating position the field is in. The Higgs boson behaves exactly like the standard model says it should. Every measurement, every decay channel, every coupling matches the predictions. But those measurements are not infinitely precise. There is room for small deviations, room for hints of compositeness, room for the possibility that the Higgs is not what we think it is. And until we can push the measurements to higher precision or build machines capable of reaching higher energies, we will not know. The unsettling part is not just that the Higgs might be composite. The unsettling part is what that would mean for the entire framework of modern physics. The standard model is built on the assumption that there is a finite set of fundamental particles and a finite set of fundamental forces. If that assumption is wrong, if particles can always be broken down into smaller constituents, then the whole project of fundamental physics might be misguided. Maybe there is no theory of everything waiting to be discovered. Maybe there is just an endless hierarchy of structures, each one made of smaller things, with no bottom layer, no final answer, just more questions, all the way down. Some physicists find that possibility liberating. It means the work never ends. There will always be new layers to explore, new phenomena to discover, new mysteries to solve. Others find it deeply unsatisfying. Science is supposed to converge on truth. Theories are supposed to get closer and closer to a complete description of reality. If reality has no bottom, if every answer just raises new questions about an even deeper layer, then what are we even doing? Are we making progress, or are we just chasing an infinite regress that will never resolve? The Higgs boson was supposed to be the final piece, the particle that completed the standard model, the answer to the question of where mass comes from, and in a sense it is. The Higgs mechanism works. Particles acquire mass by interacting with the Higgs field. That much is confirmed. But the deeper question, the question of whether the Higgs itself is fundamental or just another composite structure made of things we have not discovered yet, remains open, and it might stay open for a very long time. The LHC will keep running, the data will keep accumulating, the measurements will get more precise, and if there is a hint, a deviation, a small signal that the Higgs is not behaving quite the way a fundamental particle should, it will eventually show up. But the flip side is also true. If the Higgs really is fundamental, if there is no deeper layer, then the measurements will just keep confirming the standard model over and over again. And at some point, the community will have to decide whether it is worth continuing to build bigger machines to search for structure that might not be there. This is the shadow hanging over the field, the possibility that the greatest discovery in particle physics in the last 50 years is not an endpoint but a way station, that the Higgs boson, for all its importance, is just another step in an infinite staircase, that the universe, when you look closely enough, is turtles all the way down. No final answer, no ultimate theory, just layer after layer of structure, each one made of smaller things, stretching into distances so small that the very concept of distance starts to lose meaning. Or maybe not. Maybe the Higgs is fundamental. Maybe quarks and leptons are fundamental. Maybe the Standard Model really is the correct description of the smallest building blocks of matter, and there is nothing below. Maybe we are at the bottom, or close to it, and the next breakthroughs will come not from looking smaller, but from looking outward to the cosmos, to dark matter and dark energy, and the questions the Standard Model does not address. Maybe the hierarchy ends here. Maybe the search for ever smaller constituents is over, and the future of physics lies in understanding how the pieces we have already found fit together to build the universe we see. We do not know, not yet. And that uncertainty, that open question sitting at the foundation of everything, is what makes the discovery of the Higgs boson both a triumph and a beginning. The particle exists, the field is real. Mass has an explanation. But whether that explanation is the final one, or just the latest chapter in a story that goes much deeper than anyone expected, is still waiting to be answered. The LHC is asking the question. The universe will eventually reply. And when it does, the answer, whatever it is, will shape the direction of physics for the next 100 years. The question hanging over the field is not whether the Higgs boson exists. That was settled in July 2012. The question is whether the Higgs boson we found is the end of the story or just the opening line of a much longer one. Whether it is a fundamental particle, an irreducible piece of reality, or whether it is composite, made of smaller things we have not discovered yet. Whether it is the final answer to where mass comes from, or just the latest placeholder in a chain of explanations that goes deeper than anyone expected. And the only way to find out is to keep looking, keep measuring, keep pushing the machines to higher energies and the detectors to greater precision. Keep asking the universe questions until it stops being polite and starts giving real answers. The Large Hadron Collider is still running. It has been running almost continuously since 2010, with brief shutdowns for maintenance and upgrades. By the end of 2012, the machine had delivered enough data for ATLAS and CMS to confirm the Higgs discovery at 5 sigma. But 5 sigma is just the threshold for claiming you found something. It is not the end of the measurement process, it is the beginning. Once you know a particle exists, you need to measure its properties. How heavy is it? How does it couple to other particles? How often does it decay into different channels? Does it behave exactly the way the Standard Model predicts, or are there small deviations, hints that something deeper is going on? Those questions require precision, and precision requires data, lots of it. The Higgs boson appears in only about 1 in a billion proton-proton collisions at the LHC. 1 in a billion. That means if you want to measure rare decay channels, if you want to check whether the Higgs couples to the top quark with exactly the strength the Standard Model predicts, if you want to search for Higgs pair production, or invisible Higgs decays, or any of the other signatures that could point to new physics, you need billions and billions of collisions. The LHC has been delivering them. Through the 2010s, the machine ran at higher and higher collision rates, packing more protons into each beam, squeezing the beams tighter at the collision points, pushing the detectors to the limit of how much data they can record. By 2018, the LHC had delivered enough collisions that both ATLAS and CMS had measured the Higgs mass to better than 1% precision. 125.1 giga-electronvolts, give or take 0.2. That is close enough that the two experiments agree within their uncertainties. The mass is nailed down, couplings to the W and Z bosons measured, couplings to the top quark and the bottom quark measured. Decays into photons, into tau leptons, into W and Z pairs, all measured. And every single measurement came back consistent with the standard model. Not just close, not just in the ballpark. Consistent within the error bars with what the theory predicts. That is both good news and frustrating news. Good because it means the standard model works. The Higgs mechanism is not just a clever mathematical trick. It is a real feature of the universe. The field exists. The particle exists. The couplings are what they should be. Mass has an explanation, and that explanation is correct. Frustrating because there are no surprises, no deviations, no hints of new physics hiding in the data. Physicists did not build the LHC just to confirm what they already knew. They built it to find something unexpected, something that would point the way beyond the standard model. And so far, the Higgs is behaving itself. But the measurements are not perfect. The uncertainties are still a few % in some channels. There is room for small deviations, room for the possibility that the Higgs is not exactly what the standard model says it is. And that is where the next phase of the LHC comes in. CERN is upgrading the machine, not replacing it, not building something bigger, just making it better. The upgrade is called the High Luminosity Large Hadron Collider, HLLHC for short. Luminosity is the term physicists use to describe how many collisions a machine produces. Higher luminosity means more collisions per second, which means more data, which means better measurements. The HLLHC is designed to deliver 10 times more collisions than the original LHC, 10 times. That is the difference between a few thousand Higgs bosons in your dataset and a few tens of thousands. And with that much data, you can measure things that are currently impossible to measure. Higgs pair production, for example, the self-coupling of the Higgs field, the rate at which two Higgs bosons are produced in a single collision. This is one of the most important measurements you can make because it tests the shape of the Higgs potential, the mathematical function that describes how the field behaves. In the standard model, the potential has a specific form, and that form predicts a specific self-coupling. If the Higgs is composite, if it is made of smaller constituents, the self-coupling could be different. Measuring it would tell you whether the standard model is right or whether there is something deeper going on. The problem is that Higgs pair production is rare, far rarer than single Higgs production. The current LHC data can only set an upper limit. No definitive signal has been seen yet. But the HLLHC, with 10 times more data, should be able to observe Higgs pairs. Not easily, not quickly. But eventually, with enough collisions, the signal will rise above the background. And when it does, the measurement of the self-coupling will be one of the strongest tests of whether the Higgs is fundamental. The HLLHC is scheduled to start operations in the late 2020s. It will run for about a decade, collecting data until the mid-2030s. By the end of that run, physicists will have measured the Higgs couplings to a precision of a few % or better. If there are deviations from the standard model, even small ones, they will show up. If there are rare decay channels that hint at new particles, they will be found. If the Higgs self-coupling is different from what the standard model predicts, it will be measured. The HLLHC is not looking for the Higgs. It already found the Higgs. It is looking for what the Higgs is hiding. But even the HLLHC has limits. It is still the same machine, the same tunnel, the same collision energy. 8 tera-electron volts per beam, 14 tera-electron volts total. That is high enough to produce Higgs bosons and measure their properties. But it is not high enough to produce very heavy new particles. If the Higgs is composite, if it is made of technique quarks bound together by some new force, those technique quarks could be heavy, heavier than the LHC can reach. If there are excited states of the Higgs, higher energy versions of the particle sitting in a higher mass range, the LHC might not be able to produce them. If there are new force carriers, new bosons that mediate the force holding the Higgs together, they could be too heavy to produce at 14 tera-electron volts. To find those particles, you need a more powerful machine, you need higher collision energies, you need a next-generation collider. CERN has a proposal. It is called the Future Circular Collider, FCC for short. It would be a proton collider, like the LHC, but much, much larger. The LHC is 27 kilometers in circumference. The FCC would be 100 kilometers, nearly 4 times the size. The tunnel would be carved through the rock beneath the border of France and Switzerland, deeper than the LHC tunnel, following a path that would encircle Geneva and several surrounding towns. The machine would accelerate protons to collision energies of 100 tera-electron volts. That is 7 times higher than the LHC. At those energies, the FCC could produce particles that are currently out of reach: heavy Higgs bosons, excited states, new force carriers, superpartners, if they exist, dark matter candidates. Anything sitting in the mass range between what the LHC can reach and what quantum gravity effects start to become important. The FCC is not just a bigger LHC, it is a fundamentally different machine in terms of what it could discover. The LHC was built to find the Higgs and to search for supersymmetry. It succeeded at the first and has so far failed at the second. The FCC would be built to explore the energy range where new physics, if it exists, is expected to show up. Not because theorists have a specific prediction, not because there is a single particle everyone agrees must be there, but because the naturalness problem, the hierarchy problem, the question of why the Higgs mass is so much lighter than it should be, all point to new physics somewhere in that range. If the Higgs is composite, the FCC could produce its constituents. If there are multiple Higgs bosons, heavier ones that were too heavy for the LHC to find, the FCC could find them. If there is a hidden sector, a whole set of particles and forces that interact with the standard model only through the Higgs field, the FCC could open the door to it. The catch is that building the FCC would take decades. The current timeline, if the project is approved, is to start construction in the mid-2030s and begin operations in the late 2050s. That is 30 years from now, more than a generation, and the cost would be enormous. Estimates put the price tag at about $20 billion. That is for the tunnel, the magnets, the detectors, the infrastructure. Not including the cost of running the machine once it is built. 20 billion is a lot of money. It is not unprecedented. The LHC cost about 8 billion. The International Space Station cost more than 100 billion. Large scientific projects are expensive. The question is whether the FCC is worth it. That question is being debated right now. Not just by physicists, but by governments, by funding agencies, by the public. Because the FCC is not a national project, it is an international project. CERN is funded by 23 member states, and a machine the size of the FCC would require contributions from countries around the world. The scientific case for the FCC is strong. If there is new physics at the tera-electron volt scale, the FCC will find it. If the Higgs is composite, the FCC will reveal it. If there are answers to the questions the standard model leaves open, the FCC has the best chance of finding them. But there is no guarantee. The FCC could run for 20 years and find nothing but more confirmations of the standard model. That would be scientifically valuable. Precision measurements always are. But it would not be the breakthrough everyone is hoping for. The alternative is to build a different kind of collider, a lepton collider, a machine that smashes electrons and positrons together instead of protons. Lepton colliders are cleaner. Electrons and positrons are fundamental particles, point particles with no internal structure. When they collide, you know exactly how much energy went into the collision and exactly what came out. There is no background noise from stray quarks and gluons bouncing around inside composite particles. The downside is that electrons and positrons lose energy when they are bent into a circular path. They emit photons, a process called synchrotron radiation. The faster the particles are moving and the tighter the curve, the more energy they lose. For a circular lepton collider, that energy loss becomes a serious problem at high energies. You need enormous amounts of power just to keep the beam moving. That is why the Large Electron-Positron Collider, LEP, could only reach collision energies of about 200 giga-electron volts. Anything higher, and the machine would have needed so much power it was not practical. The solution is to build a linear collider, a straight line instead of a circle, no bending, no synchrotron radiation. You accelerate the electrons and positrons in a straight line, smash them together once, and then dump the beams. That is less efficient than a circular machine where the beams can be reused, but it allows you to reach much higher energies without losing power to radiation. The International Linear Collider, ILC, is one of the leading proposals. It would be a linear electron-positron collider about 30 kilometers long, capable of reaching collision energies of about 500 giga-electron volts, with the possibility of being upgraded to 1 tera-electron volt. That is lower than the FCC, but the cleanliness of the collisions makes up for it. At 500 giga-electron volts, the ILC could produce Higgs bosons in large numbers and measure their properties with extraordinary precision. The self-coupling, the couplings to quarks and leptons, rare decay channels, invisible decays, everything. The ILC would be a Higgs factory. That is the term physicists use, a machine designed specifically to study the Higgs in exquisite detail. The FCC is a discovery machine, built to find new particles at higher energies. The ILC is a precision machine, built to measure the Higgs so precisely that even tiny deviations from the standard model would show up. Both approaches are valuable. Both could lead to breakthroughs. The question is which one to build first, or whether to build both, or whether to build something else entirely. There are other proposals. A muon collider, for example. Muons are like electrons, but about 200 times heavier. They do not lose as much energy to synchrotron radiation, so you can accelerate them to very high energies in a circular machine without needing impossibly large amounts of power. A muon collider could potentially reach collision energies of several tera-electron volts in a ring only a few kilometers across. The downside is that muons are unstable. They decay in about 2 microseconds. That is long enough to accelerate them around a ring a few times, but not long enough to store them the way you store protons in the LHC. You would need to produce muons constantly, accelerate them, collide them, and repeat. The technology to do that does not exist yet. It is being developed, but a muon collider is still decades away from being practical. Then there are proposals for machines that do not collide particles at all. Experiments that search for dark matter directly by looking for interactions between dark matter particles and ordinary matter in ultra-sensitive detectors buried deep underground. Experiments that study neutrinos, which might hold clues to why the universe contains more matter than antimatter. Gravitational wave observatories that could detect signals from the early universe, from moments so close to the Big Bang that particle colliders cannot reach them. The future of physics is not just bigger colliders. It is a whole ecosystem of experiments, each one probing a different aspect of the universe, each one looking for the cracks in the standard model that will point the way forward. But the Higgs boson is special. It is the only fundamental scalar particle in the standard model. It is the only particle with zero spin. It is the particle that gives mass to everything else. And because of that, it is uniquely sensitive to new physics. If there are new particles out there, heavier particles that we have not discovered yet, they could show up as virtual particles in Higgs interactions. Their effects would shift the Higgs couplings, change the decay rates, produce deviations that precision measurements could detect. The Higgs is a portal, a window, a probe. Measuring it precisely is not just about confirming the standard model. It is about using the Higgs to search for what lies beyond. This is where the Department of Energy's interest comes in. DOE, which funds much of the particle physics research in the United States, has explicitly stated that the Higgs boson may be a unique portal to discovering dark matter. Dark matter does not interact with light. It does not interact with the electromagnetic force at all, but it might interact with the Higgs field. If dark matter particles have mass, and most models assume they do, then they acquire that mass the same way ordinary particles do, by interacting with the Higgs field. That means the Higgs could decay into dark matter, or dark matter could be produced in collisions where a Higgs boson is involved. The signature would be missing energy. Collisions where the visible particles flying out do not account for all the energy that went in. Something unseen carried part of the energy away. The standard model predicts a small amount of missing energy in Higgs decays. About 0.1% of the time, the Higgs decays into a pair of Z bosons, and those Z bosons decay into neutrinos. Neutrinos are nearly massless and interact so weakly that they pass through the detectors without leaving a trace. That is an invisible decay, but it is predicted and understood. If the rate of invisible Higgs decays turns out to be higher than 0.1%, that could be a sign of dark matter. Current measurements allow up to about 10%. That is a wide window. If future experiments push that limit down and find that the invisible decay rate is higher than the standard model predicts, even by a few percent, it would be one of the most important discoveries in physics. It would mean dark matter is not some exotic substance that only interacts gravitationally. It would mean dark matter couples to the Higgs field. It would mean there is a direct connection between the mechanism that gives particles mass and the mysterious stuff that makes up most of the matter in the universe. Another possibility is that the Higgs we found is not the only one. The standard model predicts one Higgs boson. Extensions of the standard model, theories that try to solve the problems the standard model leaves unanswered, often predict more. Supersymmetry predicts 5 Higgs bosons. 2 Higgs doublet models, which are used in some explanations of the matter-antimatter asymmetry, predict at least 2. If there are additional Higgs bosons, they would be heavier than the one we have already found. They might be too heavy for the LHC to produce, but they could still affect the properties of the lighter Higgs. They could shift the couplings. They could open up new decay channels. They could be produced in pairs with the known Higgs. Searching for additional Higgs bosons is one of the major goals of the HLLHC and any future collider. The implications of finding a second Higgs boson would be profound. It would mean the Higgs sector, the part of the theory that deals with mass generation, is more complicated than the standard model assumes. It would mean there are new fields, new particles, new interactions that we have not accounted for. It could point the way to a more complete theory, or it could open up an entirely new set of questions. Why are there multiple Higgs bosons? How do they interact with each other? Why does one have a mass of 125 giga-electron-volts and the others have much higher masses? What determines those masses? The discovery of the Higgs boson in 2012 answered one question. The discovery of a second Higgs would raise a dozen more. And then there is the question that no one really wants to think about, but everyone knows is lurking in the background. What if we never find anything beyond the standard model? What if the HLLHC runs for a decade and confirms the standard model to even higher precision, but finds no deviations? What if the FCC is built, runs for 20 years, and finds nothing but more standard model particles? What if every measurement comes back exactly where the theory says it should, and there are no surprises, no hints of new physics, no cracks in the framework? What then? It is not an idle question. The LHC has been running for more than a decade. It has collected more data than any previous collider. And other than the Higgs boson, which was predicted in 1964, it has not found anything new. No supersymmetric particles, no extra dimensions, no dark matter candidates, no new forces, just the standard model, confirmed over and over again. At some point, if the pattern continues, the community will have to accept that the next layer of physics, if it exists, is beyond the reach of colliders we can currently build or even envision. That the energy scales where new particles appear are so high that reaching them would require machines the size of planets, or that the new physics is not about higher energies at all, that it is about phenomena that colliders cannot probe. Neutrinos, gravitational waves, cosmology, the dark sector. This would not be a failure. The standard model is an extraordinary achievement. It is the most successful scientific theory ever constructed. Confirming it to higher and higher precision is valuable. Understanding the Higgs boson in exquisite detail is valuable. But it would mean the age of discovery in particle physics, the era when every new collider found something unexpected, might be coming to an end. That is a sobering thought. For a century, every time physicists built a more powerful microscope and looked closer at the structure of matter, they found new layers. Atoms had nuclei. Nuclei had protons and neutrons. Protons and neutrons had quarks. But that process might not go on forever. There might be a bottom, a final layer, and we might be close to it, or we might not. The universe has a habit of surprising us. Every time physicists have been confident they understood how things work, something unexpected showed up and forced them to rewrite the textbooks. The discovery of radioactivity, the discovery of the neutron, the discovery that the universe is expanding, the discovery that neutrinos have mass, the discovery that the expansion of the universe is accelerating. None of those discoveries were predicted. They were surprises, and they changed everything. The Higgs boson could be the same. Right now, it behaves exactly like the standard model says it should, but the measurements are not perfect. There is room for small deviations, and if those deviations show up, if the Higgs couplings turn out to be slightly different from what the theory predicts, if the self-coupling is off, if rare decay channels open up that should not be there, the whole picture changes. The Higgs stops being the final answer and becomes the first clue, the doorway to a deeper layer of reality. That is what the next generation of experiments is searching for. Not just confirmation, not just precision for its own sake, but hints, whispers, small signals buried in the noise that point to something new, something the standard model does not include. Something that will force us to expand the theory, to add new particles, new fields, new symmetries, new principles, to take the next step in understanding what the universe is made of and why it behaves the way it does. The future of quantum discovery is not about building one machine. It is about building an entire infrastructure. Colliders, yes, but also neutrino detectors, dark matter experiments, gravitational wave observatories, precision measurements of fundamental constants, searches for violations of symmetries that should be exact. Every experiment is a question, every measurement is a test. And somewhere in that vast web of data, there might be a thread that, when pulled, unravels the entire fabric and reveals what lies underneath. The Higgs boson was the last missing piece of the Standard Model. Its discovery in 2012 completed a theory that had been under construction for 50 years. But that completion is not an ending, it is a beginning, because now we know the field exists. Now we know the mechanism works. Now we can use the Higgs as a tool to probe the edges of what we understand, to measure things that were impossible to measure before, to search for deviations so small they require billions of collisions to detect, to ask whether the particle that explains mass is itself explained by something deeper. The universe is under no obligation to make sense to us. It does not care whether our theories are elegant or whether our experiments succeed. It is what it is, and our job is to figure out what that is. The Standard Model is the best answer we have so far. It works, it fits the data, it explains an astonishing range of phenomena with a handful of particles and forces, but it is not complete. It cannot be. Too many questions remain unanswered. And the Higgs boson, sitting at 125 giga-electron-volts, stable for less than a trillionth of a second, before decaying into a spray of other particles, might be the key to answering them, or it might not. We will not know until we look. Until we build the machines, run the experiments, collect the data, and see what the universe has to say. The search is not over. It is just beginning. And wherever it leads, whatever we find, it will be because we refused to stop asking questions, because we built the tools to probe deeper, because we looked at the smallest scales we could reach and asked whether there was something smaller still, because we found the particle that gives mass to everything and then asked where that particle came from. The answer, when it comes, will reshape our understanding of reality. Again, the way it has been reshaped every time we have looked closely enough to see what lies beneath. The Higgs boson is not the end of the story. It is the place where the universe whispers that the story goes deeper than we thought, and we are finally starting to listen. 50 years, that is how long it took to find the particle that explains why anything has mass. 50 years of theory, calculation, doubt, false starts, near misses, and machines built to the absolute edge of what human engineering could achieve. And when the signal finally appeared, when the bump in the data rose above the noise and both detectors saw the same thing at the same mass, the celebration lasted about as long as it takes light to cross the width of a proton. Because the moment you answer one question in physics, 10 more appear behind it. The Higgs boson exists. The field is real. Mass has an explanation. But that explanation raises questions that might take another 50 years to answer. Is the Higgs fundamental, or is it made of smaller things we have not discovered yet? Why does it weigh 125 giga-electron-volts instead of 10 to the 19th? Are there other Higgs bosons hiding at higher masses? Does it couple to dark matter? Is the naturalness problem real, or is the universe simply fine-tuned in ways we will never fully understand? We do not know, not yet. And that uncertainty is not a failure. It is the engine that drives the whole enterprise forward. Every answer is a new starting point. Every measurement is a test of whether the universe behaves the way we think it does, or whether there is something deeper waiting beneath. The Standard Model is complete. Every particle predicted has been found. But complete is not the same as final. The theory works within its domain, but its domain is not the whole universe. Gravity is not part of it. Dark matter is not part of it. Dark energy is not part of it. The Higgs boson, the particle that was supposed to complete the model, might